Okay, we can go ahead and hopefully everybody will join in time. We have studied very thoroughly the case of a small displacement gradient theory. That is the fact when displacement and deformation are so small that you cannot really, without some very detailed observation tools, notice the difference between the initial and deformed configuration. And basically, in this case, the key simplification that we used, given that the displacement gradient is very small, typically you say it's much smaller than 1. As illustration, I was talking about yield stress of a steel, which is a reasonable good quality of 400 megapascal, with the Young's modulus being 200,000 megapascal. The deformations of the order of magnitude 10 to the minus 3. That means really at the naked eye, you don't see the difference. In that case, what we've done is basically we dealt only with one stress, and that's the only stress that exists in the body. It was called the Cauchy stress. And basically, the big advantage of the stress in the small displacement gradient theory is the fact that although it is acting in the deformed configuration, we can pretend that it's acting in the initial configuration. And this way we could simplify the equilibrium equation being placed directly in the initial configuration. That is because when you're computing the derivatives, you're computing integrals over the form configuration. Derivatives, when you talk about the strong form, integrals also when you need this for the weak form, you can basically use the simplification that use the coordinates that are set in the initial configuration. Today we enter this, what is described in chapter 4, and this is a question of the large displacement and large deformation. So if you study now the geometrically nonlinear problem, the key point is that the displacement and deformation is so large that you can no longer pretend that there's no difference between initial and deformed configuration when it comes to computing either derivatives or integrals. Integrating over deformed configuration, which is significant and different than the initial configuration, you will not get the right result. So the key difficulty there becomes, you'll see, and that's the way I will present this development. You actually start with the same idea like in the small displacement gradient theory, because you cannot reinvent different principles. You're talking about equilibrium and either strong or weak form. But the difficulty will be that next to the unknown stress, which is reaching this equilibrium equation, either strong or weak form, you also have unknown configuration, because displacement this time is not small, and you cannot, when you need computing derivatives or integrals, simply take initial configuration. So this is really the key point. And then a second difficulty is that when you have a small deformation theory, we have shown that in 3D case, the strain measure is simply the symmetric part of the displacement gradient, and the complementary skew symmetric part is a rotation. So both of these are infinitesimal, so often we call this infinitesimal strain if there's no rotation, and both of them could be represented as like linear operator. Now, if you have a large displacement, large deformation, the kinematics, that is the equations that are giving you the ratio between the relationship between the deformation and the displacement, is heavily nonlinear. And not only that, in fact, you cannot take a unique measure of deformation. In fact, as you go along, you can see there's a very large number, in fact, infinite number of measure of large deformation. And for every measure of large deformation, there is associated stress tensor. This is just to clarify immediately, there's only one stress in reality. When you have deformed body, that's the only reality that exists. And in this deformed body, you have equilibrium, and this equilibrium is maintained by true, or often called Cauchy stress. However, as I already said, this Cauchy stress acting in deformed configuration, which is unknown, is also unknown, so you have way too many unknowns to be able to solve the problem. Hence, what you do is, especially in solid mechanics, what is important, which path did you follow to get to a particular deformed configuration, because you have this inelastic behavior, plasticity, damage, and so on. Basically, you often go back to the initial configuration, the one that you know that you've selected when you design your system or structure, and you establish the equivalent form of the equilibrium equation in this initial configuration. And that's basically the transformation that you go from one to another. And in the process, you recover, as I said, many strain measures and appropriate stress tensors that are conjugate in terms of work. And so basically, the second difficulty of large deformation is to choose which one do you want. The fact that you have many is not a handicap, it's actually an advantage, because providing a constitutive model for behavior of solid materials or fluid materials in large deformation is not an easy job, basically, because you have to deal with the very different regimes of small strain, moderate strain, very large strain, and stuff like that. So the same materials start behaving differently if you submit this material to kind of a rather different strains. So we will talk about that as well, how to kind of extend this consideration of the constitutive modeling to large strain regime. And in particular, you will see there's a much more difficulty in the small strain regime. And so one of the paths is take a principal directions and so on and so forth. We'll get to that in a moment. And then to be able to solve the problem, you have to do computing discrete approximation by using the finite element method for geometrically nonlinear problem. So I first do that for a simple Schwarz bar, and to show that the end result is a set of nonlinear algebraic equation if you assume linear elasticity, because the kinematic measure is nonlinear. And then basically you also have to go into the incremental iterative analysis and so on and so forth. Then there's a final step in this lecture that I wanted to present is that you have something in many books on large deformation, you have something called the rate formulation. In other words, instead of having like a potential and defining the free energy, people define stress rate equations. So in large deformation, you have to do this objective stress tensor rates. So something called Yauman, you have something called Truesdell, and so on and so forth. The idea is that you have to have something which is a remaining objective under large displacement, large rotation that will be invariant under superpole rigid body motion and stuff like that. So many people prefer rate theory, deal with that, but in fact, what's really behind that is something called spatial representation large deformation, as opposed to material deformation, as opposed to material representation. So I also try to explain how to switch from one to another. And basically, if you have something called material, that means you're using the object which are defined on the initial configuration. If you have something called spatial, you're using the object which are defined on the deformed configuration. So first material will be a Green-Lagrange strain, the second polar Kirchhoff stress, and spatial will be Kirchhoff stress with corresponding strain measure, and so on and so forth. So let us go into a little bit more details. So first of all, I have to say that the motivation for this one is being able to handle many different industry applications where the large displacement, large rotation would occur. And also this is leading to, in statics, to something called instability phenomena. In dynamics, this is kind of dynamic instability or called chaos. And certainly many applications to study that. For example, if you have very, let's say, turbulent flight, you have to look into the flutter instability of the airplane wing. Or, for example, right now, those who went on vacation to the part of France which is called La Réunion, they're waiting for some kind of historical storm to hit the island. So I'm sure the vacation will not be as much as fun as they thought. So, for example, taking wind load and things like that is certainly of big importance, and you have very large displacement, large rotation. Then also in the technology of many types of products, you want to look into the large displacement, large rotation, and especially failure phenomena, a localized structure. In fact, is really often related to this type of thing. And I showed you last time that you can take a cohesive length to be geometrically nonlinear beam, so you can handle these local large rotation and stuff like that. So in 80s, more precisely 84 to 88, the founder of LMT, Kershan, Jean Lemaitre, managed to gather several laboratories to work together on the research topic. They call this grande déformation et endommagement. That would be large deformation and damage. And they really produced many results that led to the writing the book by Jean Lemaitre. But for large deformation, they concluded it's enough to take the same trick like a small deformation, take a Yauman stress rate, and then you're fine. It turned out that was not really good conclusion, because there are certain oscillations that have been discovered later. And so many other places like USA and Germany, they carried on very active research. Nowadays in France, large deformation also studied for many different applications of biomaterials and like that. So if you look into typical development or what kind of references in their own domain, how to describe large deformation, you can look into either book in the series of the Handbuch der Physik, written by Trussell and Noll. It is entitled Nonlinear Field Theories. And or you can look into the book written by mathematician Jenny Marsden and Tom Hughes, Mathematical Formulation of Elasticity. Either of these are kind of scary reading, because in the first one, they use a general nonlinear curvilinear coordinates. And basically, then you look into these Christoffel symbols and things like that. And every equation has a very kind of large format. And basically, sometimes the details are perhaps clouding what is really trying to be developed. If you look into the manifold book, the goal of Marsden was to kind of show that you can use the manifold theory to develop formulational elasticity. And again, you have to get into this notation type of convention with how you actually handle with these manifolds, how you compute this derivatives, something called tangent bundle or cotangent bundle. So it's really like a vocabulary on its own. In fact, a couple of times when I was in position to coach some of the people who took, let's say, some time off, I did not study the research for a while. Typically, they were like a dean or something, and then they came back. That was the case when I was working at Polytechnique Fédérale de Lausanne. So a colleague from Liège was spending a sabbatical leave in the APFL, what is called. And he was, before working on shells, at that time I worked on large deformation, large rotation shells. So basically he came to me and said, well, what's going on? I didn't work on that for 20 years because I was the dean of the faculty, then I was a rector, and so on and so forth. And then it was still he had some active years. He wanted to come back to research. So what's going on? I said, okay, I gave him papers that were written at that time about shells. He said, what the hell, you cannot read this? What do you find vocabulary? Then I gave him a book of Marsden Hughes. He returned in 2 days, said, man, this is unreadable. Let's try to explain to me directly, otherwise I don't understand anything. So I figured, it's true that for this development, you might need these curvilinear coordinates and stuff, but for many applications, if you have large deformation, large displacement, this is taking place in three-dimensional space. So if I simply take a Euclidean metric, that is mean the real distance, I can try to describe what is going on by using the Euclidean space and not the curvilinear coordinates, just to express what is going on. And then for some developments, I might need curvilinear coordinates, but actually what we've done on shells, we showed that even there you don't need curvilinear coordinates because you can do something called local Cartesian coordinates that are certainly the shortest distance to two different points and so on and so forth. And then you simplify the implementation. This is not without importance, because if you take a finite element discretization, you have to deal with so-called locking phenomena. We already discussed this in different applications. This is an ability of the polynomial approximation to represent certain deformation modes, especially a mixture of different deformation modes. So you want to keep this expression as simple as possible. And if you have curvilinear coordinates, where even the unit vectors are not constant and the derivatives start producing something, as opposed to fixed Cartesian coordinates or derivative unit vectors are zero, then you certainly have a more difficulty picking up the right interpolation. In fact, the thesis of a person I was mentioning, I won't mention the name, he was working with Ray Clough. It was one of the last theses on shells that Ray Clough was coaching at Berkeley. It was actually developing a general shell elementary curvilinear coordinates. At the end, the main result was just to make a finite element approximation, which can represent the rigid body modes. So really, it was kind of not a big success because the locking phenomenon was so severe that you could not really handle that. But hopefully, we kind of mentioned the other type of things as we go along, and you'll see that you can do much better today. So in fact, as I said, we are placing our studies in three-dimensional space or two-dimensional plane if you talk about 2D problem. And I actually took this inspiration from a book by Philippe Sarlet, who was professor of applied mathematics at University Pierre Marie Curie. I think that ever since he retired, he went to teach in Hong Kong, and he wrote three-dimensional elasticity, where actually everything that he wrote is very nice and compact. The only thing which I didn't like, he said he did not distinguish between the matrix and tensor. Basically, he did not distinguish this way between the initial and carry configuration, because he couldn't, because he had just a representation of tensor. And basically, although the math was okay, the conceptual introduction of the large displacement was missing. And then I said, it's really a kind of not a good idea. So many of the things, when you want to do it on manifold, have been developed for the manifold on a curvilinear space. And then again, turned out to be fairly simple by using the idea of principal stretches. These are the largest value of stretches in a deformation measure, which is intrinsic. And then we developed this development for rubber-like membrane shells or elastoplastic membrane shells and things like that. So these, I think, if you're interested, you can look into these papers a little more in detail. So basically what you want to develop is a so-called no compromise development, because basically many of the people started studying large displacement, large deformation by trying to extend the development that was valid for a small displacement gradient theory with the proper way to a large deformation by heavily relying on what is already available. And in this case, they were taking not really large rotation, but they were taking like second order rotation, as opposed to what we study here is a finite rotation. This is an orthogonal tensor, which is part of a special orthogonal group of three-dimensional tensors, SO3. Or when they studied elastoplasticity, they said, okay, I develop formulation of the elastic strain is small and plastic strain is large. We said, no, we actually studied the formulation of both elastic and plastic deformation could be large. There's no reason to do that. And it's not only like a kind of purity of these developments, it's also because when you're developing something new and you don't know what will be this applied to, you want to have the most general formulation that you follow before you have to start simplifying. So if you don't have to simplify, don't. And you only simplify at the end when you have a particular application. But basically, this is really in 3D. Well, in large deformation, actually had to deal with 3D because in 1D, large deformation is not so exciting. It simply reduces to a stretch. But the real difficulty starts when you have so-called large rotation. So we do have a special class of problem that, let's say, rotations are large, but strains might be small. This is typical of structures like a please, shells, and so on. So as I said, the formulation in these classical books by Truesdell and Knoll are not suitable for finite element computation. And I cited this experience of developing general curvilinear shell element, which had difficulty representing even like a rigid body modes, simply because the curvilinear coordinates made a lots of coupling between different deformation modes. And basically, you cannot handle this correctly with the polynomial approximation. And then also, there were many simplifying hypotheses that were not really very sound for the particular application and know-how. These were written some time ago before you can do it, what you can do today. So basically, we are still studying a problem of mechanics. And even that we have very large displacement, large deformation, we still have to find only 3 groups of equation. One is kinematics, giving you a connection between deformation and displacement. The other is equilibrium, giving you a connection between stresses, internal forces, and applied forces externally. And finally, the constitutive law to give you a connection between corresponding choice of stresses and strains. They have to be conjugate in the work, in the sense of the work, and then you have to apply this. This constitutive modeling was one of the first mistakes people developing the code made, because by changing, let's say, the stress, and you also have to often change the constitutive law. If you have postulated that, let's say, the first choice of one constitutive law, and then changing to any other stress, you have to do proper transformation. This was a mistake of a very influential paper that was done some time ago. Developers, not only the original program SAP, called non-SAP, that later on became a computer code ADINA, that was given by Ed Wilson to Jürgen Barth at the end of the postdoc. So basically, the idea is that this will be just the kind of thing. And then in the large displacement, the basic source of nonlinearity is the kinematics. So we'll try first to figure out how to deal with this kinematics, how to define the state measure. In the process, you'll define more than one, so you can pick up the one that is more suitable for a description. And then we'll also show that for each and every one, there's a associated stress. In the sense that for a large deformation, these equilibrium equations are immediately nonlinear, because they have to be posed on the deformed configuration intrinsically with a true or Cauchy stress, and then transfer back to the initial configuration so you can do the computation. So we study also this constitutive model. In fact, for the large deformation theory, there are certain rules to be respected. First one is objectivity. That means when you have very large motion, you can have your frame going from one position to a very different one. And so whichever is your position with respect to this very large moving frame, you have to be observing the same physical reality. So this is something called objectivity under superposed rigid body motion. Then if you have a homogeneous material, once you have a very large deformation, the effect of homogeneity is lost, because if you compress a lot on one part and you don't compress at all, and the material is sensitive to compression, of course, the behavior can no longer be the same. So you have to be able to define what do we mean by homogeneity. And again, there's a restriction on that. So basically, the constitutive behavior, again, could be posed in terms of the internal energy, like you are doing for constructive plasticity of damage. Or you can put it in the rate form, which was the case of hypoelasticity, for example, and some of the approaches which didn't prove to be very robust. Now, the subset of these large displacement for solid mechanics is also large displacement for structural mechanics. What is structural mechanics? Well, these are the solids that have a special form, such that, let's say, some dimensions are much smaller than the other ones. If you talk about beam, that way cross-section is much smaller than the length of the beam. If you talk about plates and shells, that's a thickness which is much smaller than the middle plane, middle surface. So basically, with such a idea of being small, you can take some kinematic hypothesis to say how the strain should be varying across the thickness or in the cross-section, thing like that. And then you construct the structural theories where instead of stress, you're using stress resultants. So typical difficulty of handling those is basically large rotation. So we also look at at least a beam quickly on shells, and then to get this under control. So basically, let me first go into the kinematics of large displacement and really get all the details on that. So if this is a solid body, this is your usual sort of potato. We are placing it in the Euclidean coordinate system with a fixed basis vector, A1, E2, E3, and the coordinates of position vector given as x1, x2, x3. So the solid body for us is a collection of particles. For each of these particles, we have a position vector x. And basically, you can put this either in this vector notation or matrix notation by putting the explicit components of this vector x1, x2, x3. Then we apply the loading, which puts the solid body into the large displacement. And just actually to mention as well, I mean, since you're going to be solving again boundary problem, it is important that we have enough of these supports to turn this into the structures. That means that the gamma u boundary where you pose displacement has to have at least 3 correctly positioned points to prevent the 2 translational rotation, or in 2D, or it has to have 6 points to prevent 3 translation and 3 rotation in a 3D setting. And the remaining part is gamma sigma, where you apply the traction. Either applying 0 traction is still called applied traction. And the orientation of this boundary is done by the unit vector exterior normal that we denoted here as n. So applying the loading, we now produce a very, let's say, large displacement, large rotation. So what I picture here, in thin line, you have an initial configuration, and the thick line is the only one that is now existing, and that's the deformed configuration. So basically, what we'll do is we'll try to describe the motion. That means the trajectory of each and every of these particles traveling from the position, the initial configuration, to the position, the deformed configuration. And so this motion, we call it phi of x. It's a pointwise transpiration, not a vector field, that describes how to move a particular particle from initial configuration to deformed. In a large displacement setting, we really cannot now ignore the difference between deformed configuration. Here is denoted as omega index phi from the initial configuration, which is denoted as omega. And basically, we have to kind of decide how to describe one and the other. Now, for conceptual clarity, it is good to have different symbols, because at the end, when we do computation, we have to kind of take into account in which configuration the object that we are talking about is acting. And so the convention I took from the book of Serle is this phi, which is transformation we are looking for, on top of every object and every symbol that belongs to the deformed configuration. So this way, the deformed configuration is omega index phi, the unit vector is AI index phi, and so forth. There's nothing to stop me to keep the same coordinate system, and actually that's what we do at the end, because all the motion takes place in circular room. So if I put the coordinate system in the corner, so whatever I'm moving, I'm still in this room, so I can use all the time the same coordinate system. But taking different symbol with phi as opposed not to phi, with initial as opposed to the deformed configuration, it gives a little bit more clarity to what we are talking about. So that's why I do it. We also do this Einstein convention on repeated indices. For example, the what you call it, the position vector is xi times ei, and that sums up to x1, x1, e1, x2, e2 plus x3, e3. And all the conventions apply to any of these dummy indices, which are the same, except for index phi. So that's the only kind of animal which is exception. So basically, the question is, if I want to describe this motion, here is, I can use this position vector in the initial configuration, the one in the deformed configuration. Although they are kind of put in the same position, that means that unit vectors at the end, if I want to simplify, is simply saying that ei phi is equal to ei, or you can write it ei phi is equal to delta j times ej, and delta j being the chronicle symbol. Now, in the geometrically linear theory, when you have a small displacement, the simplification would be at this stage that x phi is almost the same as x, and the phi is very close to identity transformation. Anytime we want to compute derivative with respect to the deformed configuration xi phi, we can simply use the derivative with respect to the initial configuration xi, and integrating omega phi is the same as integrating over omega. So you see in this picture that actually that could not be the case here, because omega phi is significantly bigger, at least 2 times bigger than omega. So you cannot be integrating something 2 times as big and getting the same result. So basically, we have to decide what do we do. Given that we have 2 sets of these coordinates, we have an initial configuration and coordinates xi, and we have deformed configuration, coordinates xi phi. We can choose between 2 different formulations. One is called Lagrangian, where everything that we construct is a function of the coordinates in the initial or reference configuration, xi. They are used as independent variables. And the other alternative is take everything is defined on the deformed configuration, and independent, let's say, description is done by the coordinates in this deformed configuration, which are xi, phi. Now, typical choice for solid mechanics is Lagrangian formulation because basically we studied already plasticity and damage. If you have an inelastic behavior of a particular material, you have to know the whole path, describe the loading program with this pseudo-time parameter t in order to know to produce the stress in the final deformed configuration. So knowing where you come from, having initial configuration is really indispensable to solve this problem. On the other hand, if you take the simplest case of fluid, it's like Newtonian fluid, basically you can take that the only stress that is of interest to you is the true stress, which is in the deformed configuration of the fluid. And then the simplest behavior is assume that the true stress is proportional with the viscosity coefficient to the symmetric part of velocity gradient. And here you describe your constitutive behavior for the true stress. So really the behavior of fluids being rather simple, you can kind of afford to do that. In solids, such a behavior is not really typical. You have much more complicated constitutive behavior. You already talked about plasticity, damage, and combined type of models. And you can imagine the same thing now taken to large deformation with have different regimes. You can understand immediately that there's much more complexity in this particular case. So what does it what is it possible to do when you have a fluid structure interaction? Well, what people do, they take something called ALE, and I'll show you maybe illustration of this that we done. That is arbitrary Lagrangian Eulerian formulation. It's not so arbitrary because typically you take solids to be described in Lagrangian formulation, and you take a fluid to be described in the Eulerian formulation. So basically, this way you can have a what you call it the full description, and then arbitrary is not so arbitrary in the sense that you can have like a on the boundary between the solids and fluids, you have to move the mesh the way a solid would require, and then you apply the pressure from fluids and you go from one to another as you solve the problem. Now, this is really two basic choices, the two cleanest development, Lagrangian when you have an initial configuration to use, and Eulerian when you have deformed configuration to use. In between, in the engineering world, there were many other type of choices which are described in the reference books. For example, there's something called updated Lagrangian formulation, described in the book of Jürgen Barthe, or something called correlation formulation, described in the book of Mike Crisfield. And basically, the updated Lagrangian formulation is the idea that you want to recycle the results for the small displacement theory. So that way, you, even though that you are having large displacement that take you into the very different deformed configuration, you know that at the end you are going to do this incremental way. So what you do, you take these increments, and every increment you move your frame, and then basically you apply the Lagrangian formulation for this particular frame. So frame is moving, and there's the same thing is in the structures that Mike Crisfield described in his book on structures. Well, we call this correlation formulation because typically you have like a large rotation and you have a small deformation, and then you move the frame with a large rotation and you keep small deformation. So the end result that you can take your finite element formulation or beam or plate or shell from linear theory, and you just wrap around it large rotation of a frame, and that gives you something called geometric stiffness. We'll talk about that as we go along. So if I want to go to 1D setting, there's not much excitement, but still this could be used to explain what the large displacement, large deformation will bring. So in the thick black line, you have an initial configuration. It goes with X from 0 to L. That's the way I choose my frame. And then I have a very large deformation, typically producing the length L phi, which is much bigger than L, let's say 2 times. If the deformation is homogeneous, you can call this stretch, which is equal to the ratio between L phi and L phi being 2 times as big as L, that means stretch is equal to 2. So if I take a piece of rubber and I stretch it 2 times, I really introduce very large deformation where stretch is equal to 2. So how do I describe the problem? Well, I take an infinitesimal element in the initial configuration, I take description of the motion. Here it's 1D, so phi is a scalar and x is a scalar. I produce phi of x at the index t, t being the description of particular loading program. And then I cut the same infinitesimal element, which is now the length dx phi. And I apply the loading, b of x phi times dx phi, this distributed loading. And then I apply the true Cauchy stress. On one side, this is sigma phi of x phi plus dx phi, and the other side is sigma of x phi. And basically, then I want to set these equations. That is the first challenge, is to get this description of the motion. This is unknown. And then also to get the corresponding stress. So basically, description of the motion here, if I have 1D setting, could be done by introducing the displacement. So you can say that this point moves to that point, and this could be defined as displacement u, which is difference between the position vector x phi and vector x. So here you see that you have the interest to keep this type of choice, that the unit vectors are the same in the initial and the deformed configuration. Otherwise, it doesn't make much sense to introduce displacement. In fact, the main idea of this book of Marsden and Hughes is to say that in the manifold setting, the displacement is not defined. And you can develop all this without talking about displacement. You can develop something called deformation gradient, which happens to be defined, that you can compute derivative on the manifold without underlying coordinate system and so on and so forth. But for us to study, I will put my development in the 3D Euclidean space, and I will take the unit-based vectors. At the end, even they have different symbols to be the same. That is epsilon I phi, sorry, is equal to EJ, EI, or delta J times EJ. That is delta J being the canonical delta. So the displacement makes sense. It's different between the two position vectors. And then basically that I have to decide how to get the different configuration, how to get the stress, and so on and so forth. So in order to complete the description of the problem, I have to apply my essential or Dirichlet boundary condition. Let's say on the left-hand side, I put this to be built in. That is either saying that my displacement has to be 0 on the left-hand side, or my transformation phi at 0 has to be 0. And then the right-hand side, I either have to put the traction, which is in the deformed configuration, pi phi at time t, or in the material description, this will be like a mapping of this traction in the initial configuration. And in that case, I have to compare in the deformed configuration the true stress, sigma phi to p phi, which should be imposed. And in the deformed or in the initial configuration, I have to compare a different stress, which is so-called the first hierarchical stress, to the imposed traction. So if I do it even for the boundary condition, I have to take into account which configuration I'm using and how to define this loading. In other words, you have to be able to define, for example, how the load is changing for the unknown configuration if you don't know it, which is not so easy. So this is another motivation why I have to switch to an initial configuration. So basically, let me now try to explain the notion of the basic deformation measure, which is called deformation gradient. And I already mentioned this one works also for the manifold formulation, and in which case I don't need any displacement. However, in this case, I actually develop this by using displacement. So it's kind of more clear how this deformation gradient would arise. In particular, this is my initial configuration, this dotted line, and I apply the loading, and then the thick black line is the deformed configuration, which is the only one that exists now. And I don't want to trace anymore the real path. I simply define the motion by the displacement vector u of x, taking me from the position in the initial configuration directly to the position of the deformed configuration. Please note here, I do not follow the real path, which for the elasticity doesn't really matter. Any path I follow and I come to the final configuration, the result should be the same. And also for the incremental analysis, instead of the total displacement, I'll be dealing with incremental displacement and the notion of linearization and simplifying the formulation. Because of that, is something that we do accept without any hassle if that's really the way we compute. So again, this is just fine. Now, if I want to talk about deformation, it is not enough just to define motion of a single particle. I have to define what happens to their neighbors for each and every of these particles. Here I'm talking about local theory. That means I want to take a deformation in the local neighborhood of this particle. And the way it is described here, I take a particle at position vector x, and then I kind of find another particle which is at the short distance of the infinitesimal vector dx. So basically, one is taken by the displacement vector u of x to the new position, which is the position vector x phi, and the other is taken to a new position by the displacement vector u of x plus dx to the position which is x phi plus dx phi. Please note that further on, we will define displacement as the difference between x phi and x. And if you want to make the sense to this displacement, then the unit vectors in the initial and the configuration have to be the same. So I have the choice saying that let's say given that the position vector x is equal to xi times ei, and position vector x phi is equal to xi phi ei phi, but these two are the same. So displacement components could be written as ei times ei phi, or simply ei. Doesn't matter what I want to do, these guys are the same. Otherwise, that was the point that Marsden was making. In manifold, this is not defined because the coordinate system might not be the same. But there's a way you can build the deformation gradient directly as the derivative of the motion, which is not the case I'm doing here. What I'm doing here is the following. These are now vectors. And I can take a vector adding on top of another and coming to the final position. What's the final position? Is the point which is the farthest away from this coordinate system. So one path that I follow could be x phi plus dx phi, and I come to this point. And the other path I follow is x plus dx plus u of x plus dx, and I come to the same point. Obviously, since I come to the same point, the sum of these two vectors should be the same as sum of these three vectors. That's what I write here. So x phi plus dx phi is the same, takes me to the same point as x plus dx plus u of x plus dx. Now I take into account that x phi is minus x is equal to this displacement u. That's what I just defined, okay? And I reorder this equation, so I keep on the left-hand side all in the x phi, and write this as a dx, copying from here. X phi minus x I replace by u, and basically here I copy u of x plus dx. Then given that I have a dx, a very small infinitesimal vector that is taking me in the local neighborhood of the particle at the position x, I can take a Taylor's formula and develop the u of x plus dx as a u of x plus the gradient of displacement t u of x times dx plus the terms that are of the order dx to the power 3 and so on and so forth, which I all neglect. In terms of components, that means ui is equal to ui of x plus dx equal to ui of x plus dui dxj, the components of displacement gradient times dxj plus the terms of the order that are higher than dx. So basically, if I take this result into here, and I cancel plus u of x and minus u of x, I can pull out dx that multiplies both of these terms, and finally I write the dx phi, which is infinitesimal vector in the deformed configuration, which is sitting here, with respect to the infinitesimal vector in the initial configuration, is connected with the object which is called identity tensor plus displacement gradient tensor, and you call this deformation gradient. So the first result of interest for this development is that if you want to transfer dx to dx phi, you simply multiply this by the deformation gradient tensor f. As I said, for manifolds, you can build this directly, and you can build it as a derivative of your motion phi. And basically, what is kind of interesting is that dx is sitting in the initial configuration, or in the language of manifold, in the tangent space of the initial configuration. And basically, dx phi is sitting in the tangent space of the deformed configuration. For Euclidean setting, it's the same thing as the same tangent space of the configuration space. Basically, these two are related to the unit vectors ei, these to the ei phi. So basically, f has to be so-called two-point tensor. In other words, you can write it as a ei phi tensor product ej, and each component is equal to d phi I derivative with respect to dxj. If you write this tensor deformation gradient as a matrix, that will be 3 by 3 matrix. In the first column, you'll have 3 partial derivatives of a component of motion, phi1, phi2, phi3 with respect to x1. Then the derivatives with respect to x2 of these 3 components, and finally derivative of 3 components with x3. You can also write it by introducing this nabla, which I introduced when we talked about the 2D setting, nabla being the unit base vector EI with a partial derivative with respect to xi slammed on top of that, and phi being written as phi I times EI phi. You can then write f as a phi tensor product with nabla. And of course, displacement gradient is simply equal to f minus identity. And you can say the identity tensor here is also 2-point tensor, which you can write as a canonical delta ij, ei phi tensorial ej. And then basically your displacement gradient is again 2-point tensor, where you have the usual setting that is the 3 partial derivatives, 3 components of displacement with respect to x1 in first column, with respect to x2 in the second column, and finally with respect to x3 in the third column. Now recall in the small displacement gradient setting, we said that displacement gradient, every component is much smaller than 1, which makes phi close to identity, because these are like 10 to the minus 3, 10 to the minus 4, and here we have 1, 1, 1. So 1 is certainly much bigger than 10 to the minus 3. So if you take only 2 decimal points, you call this identity, and then you carry out your linear kinematics computation that we studied the last week. Of course, the advantage of that is that the strain measure is without any doubt symmetric part of the displacement gradient, and the complementary part, which is the skew symmetric part of displacement gradient, is infinitesimal rotation. So these two are additives, and they give you the whole displacement gradient. Now, we're not going to be using that. We're going to be using as the first strain measure this deformation gradient, and this strain measure gives you like how the infinitesimal vector of the length dx will be changing to the length dxy. So you can see it on this picture. Dxy at least 3-4 times bigger than dx. So obviously it changed a lot. You have a large deformation to get such a configuration. Now it's important to say that deformation gradient is not only the measure how the change of infinitesimal vector would occur. It's also a change of an infinitesimal element of surface. How can you compute the element of surface? Well, for example, if you take a vector product between dx and dy, both dx and dy being infinitesimal vectors, you can make infinitesimal surface element in the initial configuration. One way of writing this vector product would be to say this is dA, this is the area enclosed by this, let's say, rectangular element, and oriented in the direction of the n, which is perpendicular both to dx and dy. And then you stretch dx into dx phi, and you stretch dy into dy phi, and then you have a new infinitesimal element, which I call dA phi n phi. So connection between these two is done by so-called cofactor f. So if you know f, you can also compute cofactor. What is the cofactor? Well, cofactor is a product between f minus transpose. F minus transpose is either f minus 1 transpose or f transpose minus 1. These two things commute, and also multiply by j, where j is determinant of f. When you write your f as a matrix, you can write your determinant, and that will like this j type. So multiplying j with f minus transpose, you get transformation between a surface element from the initial to the deformed configuration. How can you show that? Well, basically, you go through this development. We just had the result that dx phi is equal to f dx, and dy phi is equal to f dy. So if you do this multiplication, turns out you need, strictly speaking, this cofactor, which is given here. That happened to be called the Nanson's formula, because Nanson was the first guy to write a paper on this. Now, we have seen that deformation gradient is giving you a change of infinitesimal vector, infinitesimal surface area, and also infinitesimal volume. Namely, if I now add on top of dx and dy, I put the infinitesimal vector dz, the mixed product, dx cross dy, scalar product with dz, would enclose this little, let's say, cube or hexahedron, and then I stretch dx into dx phi, dy into dy phi, and dz into dz phi. In this way, I produce my dV. It turns out this is just the change of coordinates formula when you have integrals. You're changing the coordinates from initial to deformed configuration. So basically, you can say the determinant of dx dy phi dz phi, which is dx phi cross dy phi dot dz phi, is equal to every of these is vectored by f. So this is f dx, f dy, and dot f dz. And basically, that turns out to be determinant of f times the dx cross dy dot dz, which is the infinitesimal volume element in the initial configuration. So you can obtain the same result by using Nelson's formula, basically by taking the distance summations to the j minus cofactor stuff. And the other guy is f times dz. So multiplying these two, you take the other side, so f minus transpose will cancel, and basically you're only stuck with a j. So this is, by the way, used in fluids. For example, if you have a mass conservation thing, you can have immediately that the mass in the initial deformed configuration is the same. That means the density rho phi times dv phi has to be the same as a rho dv, and then you have a transformation how rho phi would depend on rho through this determinant of the deformation gradient f. So you can say that the deformation gradient has some kind of intrinsic measure of your deformation, which has both, let's say, a change on the infinitesimal length, infinitesimal surface, and infinitesimal volume, and you take that as you go along. Okay. So basically, sometimes really, if I look into going back to the deformation gradient f, which is 2-point dental producing from dx the new configuration dxy. In fact, you can say that in typical modification of this infinitesimal vector, here's a picture here, not to be infinitesimal, so you can see it more easily. So this is dx, and then you slam on that f to produce dxy. So you can say that the vector is characterized by its direction, by its orientation, the little arrow that you put, and then its non-modulus. So multiplying dx by f, you change all of these, direction, orientation, modulus. But in reality, what we really care about, this direction orientation would simply give you the large displacement, large rotation, but most of the time, what is of interest to us is large deformation. So what is deformation? This is the change of the nodules or the norm of this vector. In other words, if this vector is kind of, it appears here 2 times as big as the previous vector, you can say the stretch is equal to 2. You kind of stretch it 2 times and you really introduce very large deformation. So if I now want to see how to handle this deformation directly, I can develop something which is called polar decomposition. So to explain this polar decomposition, let me look at a special case when I have like a transformation from dx to dxy, but I do not change the norm. In other words, the norm of dxy is the same as the norm of dx. So if I write this, the deformation gradient will be called r. That means something like called rotation. And then my product will be dxy is equal to r dx, so that basically I get the same norm. So what does it mean? If I take a norm squared, that will dx dot dx equal to dxy dot dxy, and then dxy is written as r times dx dot r dx. So r I take on the other side, so r on the other side becomes r transposed. So if I want these two to be the same, obviously the result is that r transpose times r should be equal to identity. Or you can write this alternatively, that r minus 1 is equal to r transpose. So basically, this is a special case where there's no deformation, where r is an orthogonal tensor. Or if you take a matrix representation, it's orthogonal matrix. It's written in terms of the cosines towards the angles and so on and so forth. So basically, if I have 2 large rotations successively, R1 and R2, I know that these rotations cannot be added on top of each other, but they multiply. So basically, the resultant rotation is equal to R2 times R1, because first it happens rotation R1, and then it happens R2. So it's not only that you have multiplication, but it's important to take into account the order of multiplication to get this fully under control. So basically, if I now want to take a more general case, I can also say that in the case where there's deformation as opposed to not having deformation, that means I need polar decomposition. I can assume that my deformation gradient could be written as the product between rotation and what we call the stretch tensor, and in particular we call this right stretch tensor because it's on the right-hand side of the polar decomposition that I denote as U. So U is a symmetric positive definite tensor. Symmetric, that means U transpose equal to U. And given that F is a two-point transformation or two-point tensor that you write as d phi dxj times ei phi tensorial ej, I can inherit this two-point feature by rotation tensor. So I write rotations are ij, ei phi tensorial ej, and then U will be then material stress measure that is written in the tangent space of the initial configuration that I write as Uij, Ei tensorial Ej. So next to the deformation gradient, I have now stretch tensor, in particular right stretch tensor, which gives me the measure of deformation directly without having to talk about rotations, unless, of course, I have to be able to compute polar decomposition to filter U as opposed to R. Now, this is one possibility, and this was sort of material strain measure, but I can also do the idea that deformation gradient could be written as V times R. Now, contrary to this one where R was on the left, here R was on the right. In other words, first I rotate and then I stretch. And so this way now, again, if R is a two-point tensor, V will be Vij Ei phi tensorial Ej phi, and basically will be sort of spatial deformation measure, which is sitting in tangent space at the deformed configuration. So here's a picture that I presented before, going from dx to dx phi. So either I first stretch it in the initial configuration, and then I take it the two-point tensor transformation R to a final position, in which case I write this as R times U times dx phi. Or I first rotate it to take it to the deformed configuration, and then I stretch it to put it in the final position, and I write this as a VR times dx. So you can see that these two are not necessarily the same. Let me illustrate this in the simple setting. So basically, for example, the deformation gradient is given as a 0, -1, 2, and 0. Can you compute R and can you compute U? So first idea is that I can write F as a R times U, with R being an orthogonal tensor, R transpose equal to R -1. So if I write F transpose F, this will basically call the C. This is so-called the right Cauchy-Green tensor C. So I take this 0, 2, -1, 0. This is a transpose times 0, 2, -1, 0. So that comes out nicely to 4, 0, 0, and 1. Then there's something called how to compute the stretch tensor from this Cauchy-Green tensor. In particular, it comes simply to, in the simple case where it's diagonal, it comes that C is equal to U squared. Or otherwise, I can write this as a U is equal to the C plus square root of second invariant multiplied divided by the first invariant of U. What invariants are? U is let's say that the sum of the results from the main diagonal, and this is the determinant and the square root of that. So that happens that if you multiply U by U, U being U transpose, you get 4 and 1. So once I have U, given that F is equal to RU, and I can take R to be F times U -1. So it's easy to obtain U -1. It's simply 1/2 and 1. Multiply by this guy, I have 0, 1, and -1. So I can see that if the large rotation is cosine and sine, this is cosine, this is sine, so I can take basically 90 degrees. It has been moved to the 90 degrees. And then given that I have U and I have R, I can now compute my V to be R times U times R transpose to get here 1, 0, 0, and 2. Now notice the difference with those two. As I said, there's two possibilities. Either you stretch in the initial configuration and then you move it by rotation to deformed configuration, or you can rotate it and then stretch it to the form configuration, you get the final result. Now, obviously here, that's if first you kind of, if you do that here with the 90 degrees rotation, you will have a component which is along x-axis. We have 2 times stretch it, and then basically rotate it to get this one. Or if you do it in the other way, where you have V, first you rotate it, and then you stretch it in the vertical axis. So you haven't changed what really happened in terms of the physical phenomena you're trying to describe, but you get a very different strain measures for one and the other. Of course, then when you're building your constitutive model, you have to take this into account. So basically, this is the type of thing that you can handle. Maybe to demystify this and try to do it, you can take to try to get this illustration for the homework, how this happens and why, and get this under control. You can get any deformation gradient and produce something that might be of interest to you and try to get this interpretation. So basically, in the process of describing these things, I have defined already 3 deformation measures, which are deformation gradient. This is right stretch tensor, and then left stretch tensor V. And then basically I can carry on and define many other deformation measures. So if you look at the typical book on solid mechanics, where they only have one chapter for large displacements, large deformation, invariably they're going to go for something called a Green-Lagrange deformation measure. How do you build that one? Well, basically, you start by appealing to a right Cauchy-Green tensor, which if you don't want to compute rotation, you can simply take into account orthogonality of R and the resultant dipole decomposition, and use this right Cauchy-Green deformation tensor to build your theory. So multiplying F transpose with F, you can take into account orthogonality of R transpose R is equal to 0, and then you can obtain that C is equal to U squared. That's actually what you got when you are computing here. Your U and C are related that C is equal to U squared. So basically, I can compute the deformation directly by using right Cauchy-Green tensor. Of course, I could have done that the other way around, but first of all, right Cauchy-Green tensor, given that depends on the right stretch tensor, is also a material measure. So you can write in terms of components C, I, J, E, I, tensorial E, J. And then you have a left Cauchy-Green tensor B to be FF transpose. With the orthogonality of R, you have V R transpose times V transpose, and it's V squared. So the left Cauchy-Green deformation tensor is a spatial strain measure, which could be written as Bij times EI phi, tensorial EJ phi. Now, as I said, for many books, which are not very elaborate on large deformation setting, they simply use only Green-Lagrange deformation, like there's no other one. In fact, this Green-Lagrange deformation is obtained in this way. You take dx phi, and you subtract dx, and then you multiply the result by 1/2. So given these results, we know that dx phi is equal to f dx. This could be written as dx dot f transpose f minus identity. And so if you take the f transpose f to be equal to c, which we thus used here, so this is equal to 1/2 c minus identity. So why do they use this? Well, the only explanation I have is if you write now this in terms of displacement gradient, then you can clearly see that you have kind of nonlinear form and a simple modification of intentional strain, sorry, because F being identity plus displacement gradient, you stick it here. At the end, you get that the Green-Lagrange strain is equal to 1/2 nabla U plus nabla U transpose, which is nothing but infinitesimal strain, plus 1/2 nabla U transpose times nabla U, which is a quadratic term here. Note that you even have only quadratic correction, but this is exact strain measure, no matter how large the deformation it is. Although it's a little bit crazy because already if you have U to be positive, imagine this now, 1D case, that is a stretch. You have something that is adding on top of it. But if you have a U that is negative, you have something, this one to be positive, this one negative. So it doesn't really change for the compression tension in the same way, because this one becomes negative for the compression, and this one remains positive, whereas for tension, both of them are positive. So something's already fishy. And nonetheless, the advantage of this is you can easily see when the large displacement and large deformation becomes small. That means that displacement gradient goes down to 0 compared to 1. This just drops off, and the linearization of the Green-Lagrange strain is equal to infinitesimal strain. And this way you can kind of build it in a way that is using using linear theory formulation and bringing it into the large displacement setting. But if the linearization was the only reason why people use it, you can linearize many other strain measures. So if I want to linearize the right stretch tensor, I can write that E is equal to linearization of E is equal to epsilon, which is equal to 1/2 nabla plus nabla transpose. And then E being equal to 1/2 C minus identity, which is U square minus identity. From here, you can say U is equal to square root of identity plus 2E. So if I want to do Taylor series development to linearize this, for example, f of alpha being a square root of 1 plus 2 alpha, that would simplify. I need f of 0, which would be 1, then f prime of 0 times alpha. So f prime would be equal to 1 over 2, 1 plus 2 alpha, and here up there would be equal to 2. So basically that becomes simply 1 multiplied by the infinitesimal stuff. So when all is said and done, if I go to tensors, linearization U will be simple identity plus epsilon. So contrary to E, linearization of E is just epsilon. Here, linearization of stretch is identity plus epsilon. So this is the measure of, let's say, translation and infinitesimal deformation. So then I can write that linearization U minus 1 in the small displacement gradient theory is just identity minus epsilon, because if you multiply U and U minus 1, you'll get identity plus epsilon minus epsilon squared. So plus an epsilon and minus epsilon will cancel, and epsilon squared will be much smaller than 1. So this is the right result for linearization of U minus 1. So using this result, the linearization of F, I can write that linearization of R, which is identity plus nabla U, multiplied by linearization of U minus 1, which is identity minus epsilon. That becomes identity plus nabla U minus epsilon, which is nothing but omega. And here nabla U times epsilon, all these are small, so you can neglect them. So I can see the linearization of the large rotation is identity plus omega being infinitesimal rotation, which is skew-symmetric part of the displacement gradient. So at the end, this is the kind of main message of the large deformation, large displacement kinematics. The coupling between rotation and deformation, you can see it in the polar decomposition, is very tight. It's multiplicative. As opposed to the small displacement, you can have actually additive coupling, because this linearizes to 1 plus omega, this to 1 plus epsilon. You develop this and you neglect the terms which are higher order, the product of omega of epsilon being much smaller than 1. And then basically you have this translation plus infinitesimal rotation plus deformation. So in one case, it's a multiplicative, and is additive, because that's what makes things a little bit more complicated in filtering deformation. So we introduced many deformation measures. That was a deformation gradient, that was right stretch, that was left stretch, left and right Cauchy-Green tensor, Green-Lagrange strain, and so on and so forth. In fact, you have an infinite number. Let me put this in 1D illustration. So if I have a bar which is plane along the x-axis, and the only deformation takes place along the x-axis, the situation theory pictured there before, then the dxy is equal to f dx, where f is written as lambda. This is stretch in the x direction, and the others are 1, 1 on the main diagonal and 0 on outside of the main diagonal. So basically, I can say that stretch is defined as a dxy divided by dx, which you can obtain as a d phi of tx, dx, which is again, one possibility to write is identity plus du dx. If you have a homogeneous deformation, your stretch is simply the ratio between the deformed length L phi and the initial length L. So if you have no deformation, the stretch should be equal to 1. So stretch is really like intrinsic measure of deformation. the most sort of easy to visualize, but not necessarily the easiest to compute. So often, you know, when we define the behavior of material, we can go for these stretches, but then we have to learn how to compute this efficiently. And that I'll show you basically as we go along. So basically, you can say that the stretch could be, if you stretch it as much as you want, you can still always be smaller than infinity. And then if you go into compression, given that the dxy is equal to lambda dx, starting from the finite value of dx, you can never squish it to 0. So lambda has to be bigger than 0. So lambda should be between 0 and infinity, and always larger than 0, smaller, of course, than infinity. So then, if you want to recover some of these strain measures, first of all, Green-Lagrange strain in 1D setting will be 1/2 lambda squared minus 1. And this is one possibility, but in fact, this is a formula of Doyle and Erickson, where they said that also Hill used this in his approach on principal direction. So it was taken back by a book called Ogden from these notes of Hill, basically saying that you can build any strain measure by starting with a stretch such that f of 1, when stretch is equal to 1, it should be equal to 0, because that's really what you want when you have a 0 deformation. Then it has to be increasing. F prime of 1 should be equal to 1, that you recover infinitesimal deformation, and f prime of any lambda should be positive. That way you have the corresponding thing. So what Doyle Erickson proposed, they said f of lambda could be equal to 1 over m times lambda to the power m minus 1, where m is not necessarily equal to 0. And then when m is equal to 0, that would be a problem dividing by 0. So we take the logarithmic strain, that is natural logarithm of lambda, when m is equal to 0. So one member of this family is a Green-Lagrange deformation. And this one, when m is equal to 0, is natural logarithmic strain. But you have a really infinite number of strain measures that you can choose this way. And then for every of these strain measures, you have to identify the corresponding stress. So this is the kind of thing on the particular strain measures. So really, that is the major complexity of large deformation. I have developed how to build the strain measures. In 1D case, they're all written here. In 3D case, they are going through either polar decomposition of a deformation gradient or directly accessing the Cauchy-Green strain or Green-Lagrange strain, so you can kick out rotation from the start. And you build anything you want in terms of these strain measures, and you can see that the major complexity would be the fact that these guys are coupled multiplicatively between rotation and strain measure. Okay, now we have developed the kinematics and different strain measures. Now the next step is to obtain the equilibrium equation and corresponding stresses. You'll see there's more than one. In fact, in reality, there's only one stress. This is called the Cauchy stress, the true stress. But then we go through the transformation from the form configuration where the stress is acting to the initial configuration. And basically in the process, we recover many of the representation of the true Cauchy stress that goes in the energy conjugate manner with the different strain measures that we discussed. First of all, let us start with the strong form equilibrium equation. So here we have an illustration. In the dotted line, I have my initial configuration, where every particle is identified with its position vector x, and I build a small infinitesimal element around this particle, let's say dx1 times dx2 if it's 2D, or times dx3 if it's 3D, and I apply my distributed load B and T, and then I take this load down to the deformed configuration, in which case the particle ends up in the new position, which is identified with the position vector x phi. And basically the applied loading would be now b phi. Now, if I take out the infinitesimal element in this configuration, and I want to keep it in equilibrium, next to applying the external load b phi, I also have to apply the true Cauchy stress, which is acting in this configuration. So obviously, this type of development allow me to build a equilibrium equation that look very much the same as I had previously. The only difference, I will stick phi to everything, just to recall that I have now a deformed configuration. So this could be written for the force equilibrium equation, that is divergence phi of sigma phi plus b phi equal to 0. And then moment equilibrium equation, which applies symmetry of the Cauchy stress, which is written sigma phi transpose equal to sigma phi. This is expressed for the infinitesimal infinitesimal element of volume in omega phi, which I write dv phi, which could be written as j times dv. If I want to see what is behind the symbol divergence phi and sigma phi, I can write this to be a sigma phi times nabla phi, and this could be written as a sigma ij phi with respect to dxj phi times ej phi. And what's written behind b phi is basically component bi phi times ei phi. So basically the idea is like, if I have this type of equation, they look identical to the small displacement gradient setting. And if I go to the from large displacement to small displacement, I simply remove the phi becomes identity, so no need to write it. And I'll get my back, I get back my equivalent equation that I had in a small deformation setting. So basically the idea that for that case, it's rather simple. I can solve the problem because the only unknowns are stresses, and your category of statically determinate problems where stress is obtained directly by, let's say, from equilibrium equations and whatnot. Now, the problem here is like a little bit different because I don't know the stress, the true Cauchy stress sigma phi, and I don't know the coordinates, which are significantly different than the coordinates in the initial configuration because of the large displacement, large deformation, so on and so forth. Another thing also, which is kind of important to say, when you're designing the structure, and especially structures in engineering domain where the dead load is something important, you're talking about, let's say, reinforced concrete 25 kilonewton per cubic meter, steel 78 kilonewton per cubic meter. But this is only the case where you have a initial configuration. If you do like, remember some years ago, there was a leakage of oil in the Gulf of Mexico. So the company doing this, I think it was Total, or no, it was maybe the Shell, whatever, one of these international companies for oil. They considered the case where you had to put like a cap built of reinforced concrete at the bottom to stop the leakage. And I forgot now what was the depth of water. So you can imagine the pressure that goes into concrete, how much compaction you can do it. So it's no longer 25, but certainly much bigger. But you don't really know upfront how much is this loading. And often you don't know what is the B phi actually. So in fact, for solid mechanics, what's more credible, not to talk about B phi, but to talk about B, that is the dead load that you apply when there's no deformation. So how do you connect these two? Well, you say that B phi per unit volume of the deformed configuration dV phi is equal to B, the unit volume initial configuration times dV. And then from that one, given that dV phi is equal to J dV, you can conclude that B phi times J is equal to B. And so given B, you can always define your B phi once you know J. Or you can go back and get the equilibrium equation not on the deformed configuration, but on the initial configuration. So multiplying this volume element by J, you will be able to replace this by V. Another thing that you can appeal to is the Cauchy principle. So if you want to get the stresses at any orientation and phi in the deformed configuration, you can say that sigma phi should be by Cauchy principle multiplied n phi multiplied by d phi. Then you take an Anson's formula that n phi d phi is equal to f minus transpose n dA. And then you merge all these things that multiply n, and you say, you call this a new tensor P multiplied by n times dA. This is not the gamma dA. So basically you get something called the first Pure Kirchhoff stress. That is nothing but the transformation of your true Cauchy stress to the initial configuration, because you're multiplying the unit vector of the exterior norma in the initial configuration. And you define the process, the first Pure Kirchhoff stress. So it turns out that in this Cauchy principle, that's not only a place where you can get this transformation. The other one, you can replace this equation here for divergence sigma. Oops. Okay, turned out, okay. Basically, I'm saying that if I take divergence phi sigma phi, and I multiply by j, so not to have it with respect to dv phi, but to have it with respect to dv only. So I will have j times sigma phi nabla phi, with the key result that nabla phi is equal to f minus transpose nabla. I can write this to be j sigma f minus transpose times nabla. So again, like in Cauchy principle, I define my first pure Kirchhoff stress to be replacement of the true Cauchy stress in the equilibrium equation that I write in the initial configuration. So basically, the key point is a little bit heavy here, but it's not so complicated in any case, that I have this result that nabla phi is equal to f minus transpose 9 nabla. That means nabla is equal to f transpose nabla phi. I can write this by saying for any function h, which is function of xi phi 1, x 2 phi, x 3 phi, I can compute the derivative with respect to xi by using the chain rule. So I have as follows. I have dh of phi xj with respect to xi. So this is dh dxi phi times d phi1 dx1, dh dx2 phi times d phi2 dx1, dh dx3 phi times d phi3 dx1. And then basically this could be written as a matrix, d phi1, d phi2, d phi3 with respect to x1 every time, and multiply by dh dx1 phi, dx2 phi, dx3 phi. I take the same result, but now the partial derivative of x2 and partial derivative of x2, 3. So what will change basically is just these terms here. So they could be written the similar way. Here I have a d phi1 dx2, d phi2 dx2, d phi3 dx3, and this vector had to be the same, dh dx1 phi all the way to dh dx3 phi. And then the final one, derivative with respect to x3, I have here d phi1 dx3, d phi2 dx3, d phi3 dx3, multiply by dh dx1 phi all the way to dh dx3 phi. So basically, when I check this, this looks like a deformation gradient. The only difference is it has been transposed. So if I take this coordinate and write it as a tensor, I can write that the vector nabla applied to any function h, which is function of x1 over 3, it can be written as f transpose times nabla phi applied to this function h. From this one, taking the inverse of f transpose, this is f minus transpose, I get that this is nabla phi to be equal to f minus transpose nabla. And that's the result that I used here when I was developing this change of the computing divergence of the stress field from the deformed to the initial configuration. So given these two results, that the load is expressed in the initial configuration. In other words, if I go back here, the true loading that acts in the deformed configuration multiplied with the unit vector, of infinitesimal element of volume is the same as this load here, B, multiplied by the corresponding representation of this infinitesimal element in the initial configuration. And the same thing here, the stress tensor, which is reacting in the deformed configuration, which goes through this divergence computation with respect to coordinates in the deformed configuration, could be replaced by using the first parallel Kirchhoff stress that goes into divergence computation in the initial configuration. And so this way I can have the final result of my equilibrium equation instead of the J divergence phi sigma phi plus J B phi. I can write this as divergence P plus B equal to 0. And also the symmetry of the Cauchy stress would lead to this result, that F P transpose is equal to P F transpose. In other words, the Cauchy stress is symmetric, but first parallel Kirchhoff is not symmetric. More importantly, you'll see that first parallel Kirchhoff is a two-point tensor. I go back to Cauchy principle. You see when you take here, you produce a vector, stress vector in the deformed configuration by using a unit vector auxiliary normal in deformed configuration and Cauchy stress. So all of them are in deformed configuration. Here, you take unit vector auxiliary normal in the initial configuration, and you produce your stress vector in the deformed configuration. So that means that P has to be two-point tensor. And you see further that he is conjugate to a deformation gradient, which is also two-point tensor, so all goes hand in hand. And basically what I've done here, to conclude, I'm, for example, going back to 1D case. So here, let's say you take your bar, which has length L, and then you stretch it, let's say 2-3 times, and you get from any position x to new position xy, which could be expressed as identity plus displacement vector. Then you take an infinitesimal element in the deformed configuration, you cut out the length of dxy, you apply your stresses sigma xy, sigma xy plus dxy, and you apply your loading b phi times dxy. In this particular case, the deformation gradient f is equal to lambda 1, 1. It's just there is a stretch in one direction. And basically by taking a Cauchy principle and in the deformed configuration and in the initial configuration, both along x-axis. So it turns out that the numerical value of true stress sigma phi at the point x phi is exactly the same as the numerical value of the first Euler Kirchhoff stress at the point x, which is kind of handy because you can, this is written here that I did it in detail. That actually means that if you want to get the true stresses sigma, you can simply in 1D case compute your stresses of first Euler Kirchhoff, and you have your numerical value of the true stresses. Although these guys are acting in the initial configuration, and the other guys are acting in the deformed configuration, in 1D setting, their values happen to be the same. Of course, in 3D setting is no longer the case because J and F minus transpose are the ones that are used to properly transform these values here. So basically, this is actually shown here. If you have a dp dx to be equal to d phi dx phi times d phi dx, that becomes lambda. So basically, this is your equilibrium equation. If you have it in the deformed configuration, multiply this by lambda because dx phi is equal to lambda dx. You want to express now with respect to dx. You take into account this transformation, and then you take into account the result for p. So that becomes dp dx plus b. It's an equilibrium equation in the initial configuration. And so this way you can really run it very, very quickly. So this is the kind of thing that you can obtain. So basically, once I've done this, the strong form, the second part is the weak form. And you'll see that in the process, I have something called the second Euler Kirchhoff stress, as opposed to the first Euler Kirchhoff stress that is done in the initial configuration. So since we have a number of pages to develop for this weak form, maybe it's we are getting close to 10-15. Maybe it's a kind of good part to take a break here. So do you have a question or comments?
No, for me, it's everything all right.
Perfect. Good. Okay. I need that one. Okay, good. Okay, so 10:30, but let's say 10:15. So basically, we can take a 15-minute break here. So let's go back and basically the idea is that we want now to see how to transform the equilibrium equation from the deformed configuration to the initial configuration, not in the spirit of the strong form but weak form. So for that reason, we have to identify, first of all, initial configuration here with the position of each particle handled by this position vector x. And then basically we have to, let me just take this one, 2, 4, 6. Okay, that's why. I keep checking, but you have, okay, that doesn't matter. So basically the default configuration then is defined as usual with the position at x phi and the motion taking the particle to new configuration with the loading b phi and the traction applied at t phi. And then in the spirit of the weak form of variation, we have to imagine the virtual displacement w phi a function of x phi. So this virtual displacement is exactly the same like we had in the small deformation setting. This is like imaginary kinematic admissible displacement. So what does it mean? It is something that is in agreement with the type of it's a small. First of all, it's infinitesimal. So even that we have a very large displacement, very large deformation, this W phi is small. So in other words, if you compute the virtual strain, they will be infinitesimal when computed with respect to the coordinates in the deformed configuration. Then they have to be kinematically admissible. In other words, if I put here the gamma u where I impose displacement, let's for simplicity assume that I have a zero displacement. Along this boundary, all the virtual displacement have to be equal to zero, because this boundary here is both initial configuration, deformed configuration, and so-called perturbed configuration. So applying W phi initially point of x phi, I have a so-called perturbed configuration. This is dotted line here. And then I can apply my weak form or equilibrium equation the way I've done it in a small deformation setting. In other words, I take a infinitesimal virtual strain that is computed as a symmetric part of the virtual displacement gradient with respect to coordinates in the deformed configuration, which is written here. So this is your infinitesimal tensor, which I compute as 1/2 dwi phi dxj phi plus dwj phi dx phi ei phi times over ej phi. And this is conjugate in terms of the work to the true Cauchy stress tensor, sigma phi, which I can write as sigma j ei phi times over ej phi. And then I have work of the external forces, W phi dot B phi integrated over the form configuration, and over the boundary gamma phi sigma, I have a product between W phi and B phi bar, the known traction applied on this boundary. The same equation written here is in this notation to give you the access to the components of this tensor that are taken here. So please note that this equation looks very much the one that we already know for small deformation setting. The only difference, you have this index phi to remind you that this time around, you have to worry about deformed configuration, which is significantly different. Here's the thick line here from the initial configuration given the thin line. And that basically you have to compute these derivatives and integrals over such configuration. Of course, that introduces the difficulty of not being able to solve the problem directly because stress is unknown, and so are the coordinates in this new configuration, because you don't know this place and you don't know the motion which takes it there. So what is the goal of this transformation? Well, to go back to the initial configuration where you might know at least configuration, and you get the corresponding picture of this true or Cauchy stress in the process of transforming my weak form or equilibrium equation to the initial configuration. So how is it done? Well, the same transformation that we just followed. Here, some remarks that I already said, maybe virtual displacements are small. That is why the infinitesimal deformation accompanying those displacement, and they are simply computed as symmetric part of the virtual displacement gradient in respect to the coordinates in the deformed configuration. So basically, the Cauchy stress are real stress that are accompanying those things. And basically, all this is written in the current configuration. So if I go down to a small displacement setting, then it becomes very simple to solve, simply because I neglect the difference between initial deformed configuration and it's done in a second. Here, I can no longer do that. So I have to do proper transformation. That means that all this virtual work equation have to be now transformed back to the initial configuration. And in process, I recover corresponding representation of the true Cauchy stress, which in the weak form is no longer first, but is now the second pure Kirchhoff stress that we denote as S. So if you imagine the infinitesimal element of the volume in the initial configuration on which you apply the distributed loading B, and basically you imagine the same type of infinitesimal volume now in the form configuration on which you have a distributed loading B phi. To keep this one equilibrium, you need true Cauchy stress. However, to keep this one equilibrium, you need the second pure Kirchhoff stress. Only this equilibrium not applied in the strong sense, in the sense that you can have just the divergence of this in the point X, but this is applied in the weak sense. That means that you're going to integrate over the configuration omega rather than integrate over configuration omega phi. So that's the difference when the transforming the strong form. So here we talk about all the time transforming the integral equation. In other words, if I have the external load, d phi acting on the virtual displacement w phi xy, integrate to omega phi. I replace dv phi with the j times dv, and j times b phi is basically b of x. And I simply do this transformation that the virtual displacement is now denoted as wx. What that means, you're talking about the same displacement that has been applied on top of your initial configuration that is sitting here, or basically even better picture here. Only here they were parameterized as a function of xy. But now we take xy to be a function of x by taking the motion phi of x, and then we can trace the w phi to become function of x through the motion. So basically that is the kind of thing that we had in mind here. So then w phi of phi of x, I then change the name, I simply call it wx. This is just the change of the name. I mean, I read many of these large displacement type of books, and what is really the most tricky thing is that in this large differential theory, one has the difficulty of understanding the difference between the function, that means the rule how you obtain something, and the numerical value of the function. So often the function has to have a different symbol for numerical value of the function, then it becomes a little bit more clear. I make this introduction of my book to kind of say that this is the bigger difficulty in understanding what is going on. So here it's a little bit kind of shady, but hopefully it is clear. So function w phi or phi of x is like composition of the two mapping. There's a function phi of x, and there's a function of w phi of x phi, and which is computed as phi of x. And this I call the new function where I kick out this phi, and I simply keep this x to be finally this different rule of how I compute this. So basically, given that I can obtain the corresponding loading applied in the initial configuration, and this redefinition of the virtual displacement as a displacement which is sitting in the deformed configuration, but it is parameterized in the initial configuration, I can very simply obtain the corresponding representation of the virtual work of the external forces, where integral is done over the initial configuration, which I now know. The same trick goes with the applied traction. So basically, I can again use this reparameterization of the virtual displacement and use a Nelson's formula to get corresponding representation of my traction forces, and then again be able to integrate not over gamma phi, but over gamma, which is a known boundary of applied traction in the initial configuration. So basically, these two results have been used already. The fact that I have a connection between the distributed loading B phi and the one in the initial configuration B through Jacobian, and I have a connection between the traction T phi and the corresponding initial configuration traction T through Nelson's formula, and this has been used in this transformation there. Now I have to do transformation of the internal work, which is a little bit more involved and a little bit more steps, but again, it's just straightforward application of the results that I already used. And that kind of is pedagogical enough to drive you through this. So you can see that the large deformation is all about applying the same principle that you already have with small deformation, plus the transformation that takes you from deformed to the initial configuration or whatever, forward or back. Often in the terminology of this manifold book by Marsden and Hughes, it's called push forward and pull back and so on and so forth. And basically this is just the transformation, nothing else. So let's go back to the internal work. This is the true Cauchy stress, sigma phi, which is a function of xy, the coordinates in the deformed configuration, multiplied by the infinitesimal strain in this configuration. This is dwi phi, dxj phi, plus dwj phi, dxi phi, ei phi tensorial ij, which you can write as w phi tensorial nabla phi plus nabla phi tensorial w phi, all this multiplied 1/2. And then basically I can first switch to this justification that dv phi is equal to j dv, and then I put j on top of sigma, expressing sigma now as a function of x. I obtain something which is called Kirchhoff stress. That one is conjugate with the material representation of the infinitesimal strain, which is now obtained as a epsilon, let's say, hat without phi of w of x. Wx being the material representation of my virtual displacement. So if I write it down, I can first of all say what that is given here. Please recall we had it just a moment ago. The key result when we're going this into a small deformation setting is nabla phi is equal to F minus transpose nabla. So I use this result again here. and saying that nabla phi is equal to minus transpose nabla, I can come here and they say nabla phi at minus transpose nabla phi at minus transpose nabla. So here I take F minus transpose on the other side. So that becomes something like W tensorial nabla times F minus 1. And here F minus transpose times nabla tensorial W. So this will be called in the agreement, basically, that you have a perturbed configuration, the one that I constructed by adding on top of a deformed configuration phi, the virtual displacement W. Here they might be multiplied with some kind of small parameter epsilon, so that I can have let's say, the corresponding value of displacement to be small. Then the formation gradient in this perturbed configuration is a nabla phi epsilon, which happens to be phi epsilon tensorial nabla. And then if you take a directional derivative of this in direction of the virtual displacement, you obtain that the variation of the deformation gradient is simply the displacement gradient of virtual displacement, which is W tensorial nabla. So basically, from this equation here, which I already had, I can obtain, this one bothers me here, I can obtain that this could be written as a nabla W, which is a virtual displacement gradient expressed now in the initial configuration, times F minus 1 plus F minus transpose times nabla W transposed. So here I have a product going back to here. I have a Kirchhoff stress, which is J times sigma, times the stuff that is written here as the product of these two tensors. Here, epsilon Wx is written as a 1/2 nabla W times F minus 1 plus F minus transpose nabla W transpose. So I don't need this result, which is very easy to show. When you have a second order tensors, here they are written as R, S, and T. So you can multiply these two tensors as a scalar multiplication. For example, if you have A dot B and both of them are second order tensor, what you take each and every component of one tensor, multiply with the corresponding component of another tensor, you sum it up for I and J from 1 to 3, and you have the sum. So this is really the way how you compute your work. You take each and every component of the strain, multiply with the corresponding component of the stress. You have from 1, 1 to 3, 3, all these 9 components. So with symmetry, actually, you have 6. And basically, you get the corresponding work. And that's what we mean by the scalar product, which is featuring in this internal force computation that is sitting here. And then you have this like a matrix multiplication. That means successive application of second order tensor upon the particular vector. So it happens to be here with the infinitesimal strain in material representation. You have it F minus 1 or F minus transpose, and you have this virtual displacement gradient with the nabla W and nabla W transpose. So basically, with the successive multiplication of these two tensors, it's actually like a matrix multiplication. In other words, when you have AB, it becomes a new tensor, which is AIK times BKJ. Summation is on the dummy index K, and then here EI and IJ. So basically, if you have this type of writing, you can have 3 different versions of the same result, which I call here A, B, and C. So these 3 second order tensors are featuring with one another, once as a scalar product and once as a matrix multiplication. So it turns out that according to these rules for the index notation, you can write R dot ST as RIJ times SIK TKG, K being the dummy index. And then without any change of anything, you can simply shift around these values because you keep summing up over the dummy indices here being K and I, and J basically to get a scalar value at the end. So I simply shift here S and R first, and then take other T. That means first I take a matrix multiplication of these tensors S and R. So according to these rules, there's something which is really not going correctly because they should be summed up on this index, not on that one. But that simply means that here you have to have S transpose times R because they're summing of this guy. And then I have a scalar product because now K and J being the free indices, they sum up on both K and J, and I have my scalar value, which is the same as the first one. And finally, if I shift this first to R and T and leave S, That means they are now into matrix multiplication and they are summed up with S. So this is the result that I need. I call it A, B, and C to work on these two terms. In other words, I have here started from the deformed configuration, infinitesimal virtual strain times the true Cauchy stress. They've been reduced to material representation of this infinitesimal strain times the Kirchhoff stress times dV. And this was the explicit form of this infinitesimal virtual strain written in material representation. So now I make the combination. So this is called R, S, and T, these three tensors that I just talked about. And I say this combination of A and C, which allow me to take this F minus 1 and move it on the other side, so that it becomes F minus transpose. And I just copy nabla W dot tau times F minus transpose. Whereas this one combination of A and B would allow me to move this on the other side. So it becomes nabla W transpose dot F minus 1 tau. Then I can take this result without changing anything. I can insert F minus transpose F transpose, and here F times F minus 1. And then I play the combination A and B to get rid of this F minus transpose. So I'm stuck here with F transpose W dot F minus 1 tau F minus transpose. And I again here insert F minus 1 and I play combination of A and C. And I get nabla W transpose F dot F minus 1 tau F minus transpose. And then basically these guys are the same. So F minus 1 tau F minus transpose is actually multiplied when I sum it up to 1/2 F transpose nabla W plus nabla W transpose F. It happens to be, this is nothing but variation of the Green-Lagrange strain. And what we call here F minus 1 tau times F minus transpose is called the second pure Kirchhoff stress. So let me make comments a little bit on that. So second pure Kirchhoff stress is produced from a directly Cauchy stress, which is equal to J times F minus 1 sigma F minus transpose. And obviously you can have this one to be a spatial stress pulled back, what is called to the initial configuration to get a material representation of this true stress. And then this is variation of the Green-Lagrange deformation, because recall the variation of your F is equal to the displacement gradient of the virtual displacement. So every time you have a variation of F, you have a F transpose, for example, the first one times variation of the second, that will be variation of displacement, virtual displacement gradient. And this will be variation of the first will be W delta nabla W transpose times F. And again, this becomes something that is a variation of your Green-Lagrange deformation. So when all is said and done, I can start with a spatial description of the virtual work of the internal forces to get corresponding material description of the virtual work of these internal forces, in which case the true Cauchy stress is replaced by the second pure Kirchhoff stress, and the infinitesimal strain of virtual displacement is replaced by the variation of the Green-Lagrange strain. Please note this variation of the Green-Lagrange strain is still function of the real motion, because now it gets more complicated given that you have this transformation going back to the initial configuration. But this is kind of normal because, you know, here you had something which was fully described in the form configuration, being infinitesimal. So you have nothing else but the symmetric part of the virtual displacement gradient with respect to the coordinate in the form configuration. Inconvenience that you don't know those coordinates, making translation back to the initial configuration, you get your transformation there, and then you have to stick with this nonlinear expression. So in conclusion, what I just explained to you is basically that if I want to recast the virtual work equation in terms of the initial configuration, I end up having internal work expressed as a second pure Kirchhoff stress, paired in terms of the work with the variation of the Green-Lagrange strain. And then work with external forces is the material representation of this virtual displacement with respect to the material representation of the applied load and applied traction. So the principal virtual work has been now expressed in the initial configuration, and Green-Lagrange equation came as a deformation came as a work conjugate, let's say, to the second pure Kirchhoff stress. So I have two stress tensors. The first one is replacement of the true Cauchy stress in the strong form, and the second one happened to be replacement of the true Cauchy stress in the weak form. And I can now go to let's say variation of this thing to show that, and we already went through this, so I'm not going to repeat it. So basically, as a conclusion of these different things is that if you want to express the work of the internal forces, to every strain, you have a corresponding stress. If you have a true Cauchy stress, you need an infinitesimal strain in the form configuration. If you need a Cauchy stress, you need infinitesimal strain with the material representation. And if you have a second pure Kirchhoff stress, you need like a variation of the Green-Lagrange strain to be conjugate to that. So basically, we have said that second pure Kirchhoff stress is replaced in the weak form with the first pure Kirchhoff stress, which is equal to J times sigma F minus transpose, as opposed to S being J times F minus 1 times sigma F minus transpose. So these two stresses are not the same, and they should not be, because one is replacing the true stress in strong and the other one in the weak form. However, even if you did not think that the first pure Kirchhoff stress is a natural replacement of the, let's say, the true stress in the weak form, it's very easy once you understand this transformation to see that you can actually do it. Namely, I start with this transformation where this expresses the variation of the Green-Lagrange strain times the second pure Kirchhoff stress. And then I take into account what is the connection between S and F and P, sorry, to be that S is equal to F minus 1 times P, or P is equal to F times S. And then I also take into account what is the variation of this. It's 1/2 nabla W transpose F plus F transpose should be times nabla W. And so then I take the combination of the results A, B, and C. Recall this was the idea here of these three tensors. One of them are first a matrix multiplication, then you have a scalar product. So combination A and C would allow me to put the S on the other side, F on the other side. So that becomes S times F transpose. And basically, if you take F on the other side, that becomes something like a S times F transpose. And the idea is that in this case, S is a symmetric tensor. So S transpose is the same as S. So I can add this to be S transpose F transpose. But this is nothing but my P transpose by this definition. And here F times S is also equal just to P. So summing up these two things, you know, scalar product between the tensors is the same as scalar product between transpose of the tensors. So 1/2 and the 2 times would cancel. And you show that basically the variation of the deformation gradient, which is the virtual displacement gradient, and the first pure Kirchhoff can also be used to express the work of the internal forces. So although the first pure Kirchhoff has not been used to write the weak form, if you know how to do that, you can also use it to express the weak form. Typically, as I said, depends on the particular application. For example, in develop the shell theories, working with Paolo Clemente, I know that he always uses first pure Kirchhoff stress because that happened to be this phase to and the shell theory and so on and so forth. So basically, if I go to a 1D setting, let me try to explain a little bit this in a more simplified manner. So if you have a simple bar, it goes from a length L to the length L phi, that your deformation gradient is, let's say, constant. So you have a homogeneous deformation field. You write your deformation gradient as lambda, which is the ratio between the deformed length and the initial length, and then 1 and 1 on the main diagonal, and 0 all the other terms. So F minus 1 is the same F minus transpose. It can be written as the 1 over lambda, 1 and 1 on the main diagonal, and 0 all other terms. And J is determinant F is simply equal to lambda. So different stresses are here. If I have a true Cauchy stress, it has only one component, sigma. So the Kirchhoff stress is equal to J times sigma, J being equal to lambda, it's simply equal to lambda sigma. The first pure Kirchhoff is J times sigma times F minus transpose. F minus transpose being 1 over lambda, J being lambda. It turns out that the value of P is the same as the value of sigma, this one being in the initial configuration, and this one being in the deformed configuration. And then finally, second pure Kirchhoff is J F minus 1 sigma F minus transpose. So these guys being 1 over lambda and J being lambda, you end up saying that the value of S is equal to sigma divided by lambda. So you can write work of the internal forces either as the true stress times the virtual displacement with respect to the deformed configuration. You transfer this into the initial configuration. You get the value of the real stress in the material configuration is the same as P, and that becomes dW dx, integrating over the initial configuration. Then you can either divide by lambda and multiply by lambda here, so you don't change the expression. So that becomes a the Kirchhoff stress multiplied with the material representation of the virtual strain. And then finally here you can divide by lambda, here multiply by lambda. And that becomes your second pure Kirchhoff stress multiplied by the variation, what you'll see is a Green-Lagrange strain. In fact, this is what you get, is one is a variation of the deformation gradient. The other one is a variation of the natural logarithm of deformation gradient. And then the last one is a variation of the Green-Lagrange strain, which is 1/2 f squared minus 1. So basically, by taking into account what it is, I can then say that the internal energy is here the product between F and P, F being conjugate to the first pillar Kirchhoff stress, or the Kirchhoff stress tau and the natural deformation, which is the natural logarithm of the stretch. And then finally, second pillar Kirchhoff stress and the Green-Lagrange strain, which is 1/2 lambda squared minus 1. So this is the way I can write the internal work of the virtual work as 3 different ways with different stresses and different strain. So this really kind of explains all the stuff that you can do in terms of the type of stresses, and you can see that a number of these stress tensors have been introduced, and if you start using rotation, you have something called biostress and so on and so forth, which is used for shells. We'll talk about that. So once I've defined kinematics being a major issue of nonlinearity, and I define the equilibrium equation both in strong form and weak form, giving rise to a second pure Kirchhoff for the weak form and first pure Kirchhoff for the strong form, I have to complete my development by saying I need now constitutive behavior. So given large diversity of the strain measures and given large diversity of the corresponding stresses, the question is, what do you mean by elastic behavior? Namely, there are many choices. You can start with the first or second pure Kirchhoff or whatever it is, all the strain different measures, and you say this is the Hooke's law. So among different possibilities, I took this from a book of Sadler. He found somewhere that you call this Saint-Venant Kirchhoff material. So basically, this is the constitutive model where you take Hooke's law applied to a second pure Kirchhoff stress and Green-Lagrange deformation tensor. Probably he looked into many books on a very small chapter on large deformation where they took Green-Lagrange strain and then they took Hooke's law on top of Green-Lagrange strain, which give you the second pure Kirchhoff stress. So then I stick to that. Although as far as I know, neither Saint-Venant nor Kirchhoff ever invented any material of this kind, but probably they put these names in honoring the contribution of these 2 scientists. And basically, so imagine if we now take such a behavior, so I can define second pure Kirchhoff stress with the Hooke's law, and I need the elasticity tensor just like for the small deformation setting, which is defined in terms of, say, Lamé parameters, lambda and mu. So I can this way obtain that S is equal to lambda times trace Green-Lagrange strain times identity plus 2 mu times Green-Lagrange strain. In terms of components is given here. Then these Lamé parameters are written here. In terms of Young's modulus and Poisson ratio, and I can then go along and compute those values or either I can replace this lambda and mu by corresponding Young's modulus and Poisson's ratio and so on and so forth. So let's see if this is kind of good choice. First of all, it could be a good choice if as I said, if you postulate that this hyperelasticity, but you can also allow to have a internal energy, like we're doing plasticity and the damage and so on. Always ingredient, one of the ingredients was internal energy. So if I assume this to be quadratic form in terms of Green-Lagrange strain, I can define internal energy to be a strain energy density is equal 1/2 E dot CE, where E is Green-Lagrange strain and C is elasticity tensor. So if on top of that, I allow that external forces come from the potential, in other words, that I have some kind of potential which gives me the external forces to be a derivative of this potential with respect to the configuration, and then surface force is the same thing, then I can say that I can build the whole total potential energy in terms of, let's say, strain energy density W, and then these potential external forces, and hopefully I can count on the principal minimum of total potential energy. And principal work will be obtained as the first derivative or Gatta derivative respect with the virtual displacement and so on and so forth. But this is for the case where the things go smooth. In other words, where I do not have instability phenomenon. What are instability phenomena in large displacement setting? Well, that's the case when you have very large displacement, you can come to the configuration which is critical, which is characterized with the instability, where the small perturbation of the equilibrium might lead to very large motion. And then typically talking about buckling or nonlinear stability and stuff like that. And I want to illustrate this as one of the features of this type of a problem. So if you go through this and you exclude the possibility of instability, then you can have this minimum total potential energy and basically get the stuff for some non-Kirchhoff material. However, if you really want to assume whether this some non-Kirchhoff material is physically justified, then one has to look into the extreme cases. What I call extreme cases, this is the case where you recover the infinitesimal strain. In other words, we already said that one of the major advantages of a green Lagrange strain is that it is written as an infinitesimal strain plus quadratic update of this infinitesimal strain. So it's obvious when you're linearizing, this quadratic update will drop and green Lagrange strain will be reduced to infinitesimal strain. If you look how we computed the conjugate stress, which is second pure Kirchhoff stress to this green Lagrange strain, as product between J, the deformation gradient determinant, F minus 1 times sigma F minus transpose. So linearizing, F will go down to identity, J will go down to 1. So you do recover your stress tensor of the true Cauchy stress. And then your linear constitutive equation for the large deformation, some Kirchhoff material, we reduce to usual Hooke's law for small displacement gradient theory, like sigma equal to C times epsilon. So this is just fine. However, if I have another extreme, I have a very large motion, and let me show it here. I have something which is, a one-dimensional case is F is equal to lambda, one domain diagonal, 0, and your lambda is a stretch. This is like L phi divided by L. So U being the displacement of the free axis will be equal to 1 plus U over L, and J will be equal to lambda. So then I can see that the true stress, which is a Cauchy stress, which has the same numerical value as the first pure Kirchhoff stress, can be obtained by this some Kirchhoff material. First of all, for the second pure Kirchhoff, it is equal to E times 1/2 lambda square minus 1. And then P would be equal to lambda times S. S is missing here. And it becomes E times 1/2 lambda square minus 1. So basically, let me illustrate this a little bit better. What could go wrong? So if I have such a case, so this is my bar. It has length L. And I fix it on the left-hand side. Then I stretch it to the new length L phi. With what we said is I have orientation of the x-axis given this way. So my deformation gradient is equal to lambda, lambda being the ratio between L phi and L, then 1 here, 1 there, and then the other terms are equal to 0. We said that the value of P, which is, so here determinant F is equal to lambda, and then F minus 1, F minus transpose is simply 1 over lambda. Here's 1 and 1, and all the others are 0. So P of x is defined as J times sigma. You can call it phi of x times F minus transpose. That means that the only component of P, so if this is the tensors, I can write that the only component P of x, the numerical values will be the same as this sigma. So if I have a second pure Kirchhoff law, this is S is equal to E, which is Young's modulus, times 1/2 lambda squared minus 1. This is your green Lagrange strain in terms of these stretches. So P is equal to F times S. Here, this becomes a single component will become lambda times S. So that becomes equal to E times 1/2 lambda times lambda squared minus 1. So now I go into this limit cases, and that becomes like the same value as a true Cauchy stress, because this is really the kind of judge for a real physical behavior of the material. I mean, you cannot judge the value, what's going to happen in terms of plasticity or other things, by looking into these different pictures of material. You have to go into the really physical kind of stresses, the ones that are really acting in your deformed body, in order to get the proper impression what is the kind of behavior that you can have in this particular kind of case. So basically, the idea is like if I have that, I can take into account what happens when lambda goes down to 1. That means there should be no deformation. I can get that my true stress, sigma, should go down to 0, as it should, because Hooke's law is correct. Then if I have a very large stretch, I'm extending the bar 10, 100 times, let's say going here to infinity. Basically, with this constitutive equation, lambda will go to infinity linearly, lambda squared will go to infinity quadratically. I can say that the sigma will also go to infinity. In other words, physical observation, which is entirely correct, is that if I really have to introduce a very large strain or reasonable material, I have to put very large stress. Otherwise, you don't do that so simply. But you can also go into compression, in which case, your LV will be a compression, and LV will be actually smaller than F. LV will be smaller than L, because you are in compression. So what is the limit? Well, you cannot completely reduce it to 0, but you can go towards the 0. You squish it as much as you would. And so with lambda going down to 0, it turns out that basically P, or true value of sigma, also goes down to 0, which is a bit crazy, because here you have this goes to 0, so it's -1, but this goes to 0, so it goes to 0. So this is really completely wrong. So what the hell is this? And how can we get that? Well, basically, the idea is that you can compute when the thing go wrong. You can compute what is the derivative of P with respect to lambda. And you can see that this derivative is computed as E times E divided by 2. Here we will have like L to the power 3. So that becomes 3 times L squared. And then this one will be minus lambda, so it becomes equal to 1. So if you now ask this to be equal to 0, you'll obtain there's a lambda, which is equal to 1 over square root of 3, or if you want square root of 3 over 3, which is 1.73 divided by 3 is something like 0.5 or something like that, 5.7 or something like that. And then you can obtain what is, let's say, the P minimum as a function of this. You go back into this and you obtain this value to be equal to E times 1/2. And here you have 1 over square root of 3 multiplied by 1/3 the minus 1. And you have really like a minimum stress. So basically you can have like a stress strain diagram, which looks like this. Here's your lambda. Here's your sigma, which is the same as the value of P. So you have at lambda equal to 1, you have 0, and that one goes to infinity. So the proper behavior should have been something that one goes to minus infinity, but instead of that, at the value which is equal to 1 over square root of 3, you have inflection point, and this one turns into a 1 and then goes down to 0. So that happens to be a stress rate diagram for some benign Kirchhoff material, and obviously that doesn't make any sense. Basically, you have the result that means that if you have very large compressive deformation, you need zero stress to apply this deformation, which is certainly not physical. So what's the conclusion? Well, this some benign Kirchhoff material cannot be used for very large compressive strains. In fact, all the strains that are below this value of 1 over square root of 3 for the stretch, you have a problem because you go into some kind of softening, which is completely unphysical without any plasticity or fracture failure, and you get to that. Nonetheless, this was the material which was very much used into many books on plates and shells. So why was that? Well, because when you have a plates and shells, you have a large displacement, large rotation, but very small strains. So you end up having only this type of region to use, either large compressive or a small compressive, small tensile strain, and then basically you are still fine because some Kirchhoff material would stay in the let's say neighborhood of the linear type of constitutive model, and you can handle the large displacement, large rotation properly with the Green Lagrange strain. But if you had the application, we had to have like a very large compressive strain for any reason that you want to study that, please know that this type of material is not going to be the proper way of doing it. So this is what I said here. It's stated here when lambda goes to 1, p goes to 0, it's fine. Lambda goes to infinity, p goes to infinity, it's fine. But when lambda goes to 0, and that means u goes to minus L, you completely squeeze the bar. It turns out that you need like a p to be equal to 0. And so you can obtain this minimum value of the stress that you can go below that, which is equal to minus 1, 3 times square root of 3 times e. And this is about it. So basically what happens here is that what went wrong, this is your stress strain diagram. You have this inflection point at 1 over square root of 3, value of stretch, and then basically your energy, which should be going up to infinity, turns out and blocks the other way. And then basically what really you lose convexity with respect to stretch. So then there was a rather well-known work of a British mathematician, John Ball, where he said if you want to devise a proper constitutive model for the large deformation setting, let's say the best way is to look into the intrinsic measure of the strain, which is given by the deformation gradient. Then that gives you a transformation of the infinitesimal vector from the initial to the deformed configuration. Then the infinitesimal surface element that is given by the cofactor, which is equal to the determinant J times F minus transpose, or transformation of the infinitesimal volume, which is given by the determinant equal then to J. And so basically, if you build a convex structure with respect to F, cofactor F and determinant F, then you can be sure that physically you're going to be transforming the energy always correctly. You will have this proper behavior in the limit with the large compressive strain accompanied with large compressive stress, the large tensile strain accompanied with large tensile stress, and so on and so forth. So one of these models which were able to be constructed for the rubber-like material by using this approach of a principal axis is Ogden material for the rubber. And then you can actually work out this systematically for many other cases because in terms of principal stretches, but again, this is the work that was already advocated in Hill, only in the notes of the course, but never got published in that sense. So we were developing many of these things. For example, this is large deformation of rubber. This is something like an incompressible material. So the deformed configuration, which is basically stretched 2 times with respect to initial configuration, the volume should be the same as the initial configuration here. And that's basically the one that they can apply. So, okay, once I have obtained the kinematics, equilibrium, and constitutive equation, I want to go and see how I solve the problem by using the finite element setting. So to start with, I'll take the simplest possible case, again, 1D bar. But contrary to small deformation setting, I cannot be happy just following the displacement in the x direction because the large displacement is strictly characterized by the large rotation. So if you really want to bring all the power of this formulation, you have to at least to consider 2D problem. And so not only 1D, but 2D type of formulation. So basically, I claim that you have only one displacement, so one strain component. This is a E11, and one stress component S11. This is some kind of cable, but its cable is capable of representing the stiffness also in the lateral direction. So how come that is possible? Well, it's not so difficult to understand. If I take this sheet of paper and I put it under the dead load, so the sheet of paper is so, let's say, flexible that it cannot even sustain its own loading. However, if I now pre-stress this, in other words, I introduce the initial stressing here, I can take any weight like this pen here, oops, and basically I can keep the weight in the transverse direction, see with the pen on top of that, by basically keeping something with pre-stressing. So basically you have a unique property of the geometrically nonlinear problems that next to the usual stiffness concept, you have something called geometric stiffness, that basically this pre-stressing will turn the structure able of undergoing certain strain. And I'll give you maybe homework to look into that, how this is handled. So describing a situation of this kind, I apply the virtual work method to a bar, which is initially of the length L, and the work of internal force is expressed as a single stress component times a single strain component. And here you have the loading, which could be applied in both directions, because I said the pre-stressing can give you the stiffness, and also traction, which can be applied in both directions, x1, x2, again, with the pre-stressing to give you the stiffness. So my 7-9 kickoff material that I use here for simplicity, it's a little bit messy, but what the hell, it's clear enough, I hope. The only one stress component, S11, is equal to E, which is Young's modulus, times the only one strain component, which is E11. So this strain component in 1D setting can be expressed as a du1 dx. Dx is the same, x is the same as x1, times 1/2 du1 dx squared plus du2 dx squared. This is quadratic update of the Green-Lagrange strain, the phantasmal strain that we had there. Then I take variation. So from du1, I get w1. From this one, I get du1 dw1. And from this one, I get du2 dx times dw2 dx. So 1 plus du1 dx is equal to d phi 1 dx, and the other one is simply d phi 2 dx. So I can write it also in this manner. So I plug this into the work equation, and of course now I have to do interpolation. So I go for the same interpolation I used before. Let's say I start with a two-node truss bar element, which has these shape functions which are linear on top of each element. They start with the unit value at node A and 0 on all the other nodes. So I can write it this way: x minus xa divided by the length of the element to the left, La minus 1, and then a plus 1 minus x divided by La, the element of the length of the element to the right. And basically, I can then build my interpolation of displacement as the sum of the shape functions like that, multiplied by the nodal rays of displacement. I build that for both horizontal and vertical component. And at the boundary, I impose displacement, which is the last node. Here we took this a little bit differently. We took it on the right-hand side. I have to add this nn plus 1x times impose displacement, either x or y direction. And then virtual displacement obtained by using the same shape functions multiplied by the unknown values of virtual displacement nodes. And these values are 0 only at the nodes where I impose the displacement. That means here the last node. So I only have n terms that I take into account. Then I plug this interpolation into the computation here. So I need derivatives of u1, u2, w1, w2. It's easy to obtain derivative of these shape functions. And I obtain something like a derivative dna dx, dna dx. This is coming from the virtual displacement multiplied by the nodal laser virtual displacement parameters. And here you have expression for your stress. Basically, that you have, first of all, from the virtual strain, there's a dnb dx times 6b plus db1, db2. These are the real displacement times S11, which is function of some kind of displacement field, and basically minus the work of the external forces. In fact, by using this interpolation, you come up with the final product of finite discretization, which is a Galerkin equation, which expresses the equilibrium equation in the weak form in terms of the unknown parameters of a displacement field, and the residual are a comma I in direction of the axis xi for any arbitrary value of the displacement of the virtual displacement at the free nodes has to be equal to 0. So when all is said and done, I can conclude that each of these residuals have to be equal to 0. So I come up with a set of nonlinear algebraic equations where I have a equivalent nodal loads for the internal forces, equivalent nodal loads for the external forces, matching each other. So basically this one is already linear function of displacement. You'll see in a moment, S is a quadratic function of displacement because Green-Lagrange strain is quadratic function of displacement. Multiply by Young's modulus, you still have a quadratic function of displacement. So together you have nonlinearity, which is kind of a cubic equation for this type of thing. And this is typical of these. So then I can go to a usual finite element discretization. In other words, instead of taking Galerkin method with a global point of view of how to construct these shape functions, I take an elements-wide representation, and I take element by element type of thing that I have to take and obtain the corresponding value of the say element stiffnesses, internal forces, external forces, and so on and so forth. So I focus upon particular element that goes from node A to A plus 1, and I take shape functions that belong to nodes A and A plus 1, and I do, instead of global description where everything is expressed in terms of these coordinates in the initial configuration with the coordinates xa and xa plus 1 for two nodes, I turn this into local description so that xi1 is minus 1, xi2 is plus 1. Again, it was taken for needs of numerical integration. Then the nodes which are on any truss element globally placed A and S plus 1. Here they become 1 and 2. Degrees of freedom were before dA 1 and 2, dA plus 1, 1 and 2. Here they become D1, 1 and 2, D2, 1 and 2. So the first index is the node, and the second index is the direction in which you go. So comma in between is there, but what the hell, it should not be interpreted as a partial derivative. One has to understand notation of that as you go along. And then shape functions, which are function of x, are now expressed as a function of xi, with xi being the natural coordinate. So now you can say that my representation of geometry is done in terms of these natural coordinates. So x of xi is equal to an a of xi, which is 1 of plus 9 xi, minus 1 for the first node, plus 1 for the second node, times the corresponding coordinates x1 and x2. So the Jacobian becomes like a derivative of such a function x of xi. It simply becomes x2 minus x1 divided by 2, x1 being right node, x2 being x1 being left node, x2 being right node. So basically it becomes length of the element divided by 2. And so the derivative of shape function with respect to x becomes 2 over LE, the LE being the length of the element, multiplied by the derivative of NA with respect to xi. So once you have obtained the representation of your initial configuration with the natural coordinates, you take the same interpolation for the displacement field. And so basically you can see that in large deformation, it's quite handy because the form configuration xy is simply now the sum of these displacements and the corresponding coordinates multiplied by the same phase function that you want to obtain. So anytime we need it here, for example, you need a Green-Lagrange deformation, which could be obtained as du1 dx plus 1/2 du1 dx squared plus du2 dx squared. So dn1 dx becomes 1 minus L, dn2 dx becomes 1 plus 1 divided by L. So it becomes 1 over L, and we write it like that, minus 1, 0, 1, 0, multiplied by all the value of nodal displacement. This is d1 in the direction 1, d1 in direction 2, and then d2 in direction 1 and 2. So I can write this as coordinates in the chosen coordinate system where x is placed along the x of the bar, where the L is equal to x2 minus x1, and the difference between y2 and y1 is equal to 0 because both of them are 0. Initially, I'm talking about the element which is placed along x-axis. So I can write it as a x E transpose, where x gathers all the coordinates on two nodes for the node 1, x and y, and for node 2, x and y. And this matrix H is equal to a unit block identity matrix, so it becomes 0, 1, 1, 0. And then again, the same block here, and here's like the same identity multiplied by minus 1. And all this is divided by LE squared, so this way I get my corresponding value of du1 dx. So then I can compute let's say this value written this way, and basically these two putting together, I obtain something like 1/2 squared d E transpose H times dE. So here you know that you have only X, and here you have a D in both sides of a quadratic term. So when these two results are together, adding together, for the first one here being 1/LE squared XE transpose HDE, and from the second one being 1/2 LE squared divided by LE squared D transpose HDE, I have my final interpolation for the Green-Lagarde strain. You can see this is a quadratic function or the nodal values of the displacement. Then I multiply this by, of course, Young's modulus of the stress. I will need also virtual strain, so they could be obtained by this interpolation. So first term will be X transpose HWE is the same as this one, only W is changing the D. And then you have an extra term here, which is 1/LE squared DE transpose H times VE. So the virtual strain becomes 1/LE squared X transpose plus D times H divided by W, or multiplied by W, sorry. So putting this into my interpolation, what I obtain is the first part. This is interpolation of my virtual strain. And then I have my interpolation of the stresses, which is again, interpolation of the Green-Lagarde strain multiplied by Young's modulus. So I can see that the virtual strain is the constant value in the two-node truss-bar element that depends linearly on the real displacement. So I take it out of the integral. I can see that the second pure and Kirchhoff stress component, the only one which is not equal to 0, is quadratic function of the nodal displacement, but it's also a constant, so I can take it outside of the integral. So this integral becomes, there's a LE squared, so I take one LE here, one LE there, and I just have integral over LE dx, so it becomes LE, so LE divided by LE is 1. So at the end, all is said and done, I have internal forces to be equal to H transpose 1/LE x plus D times S11. This is how I compute my internal force. And basically, if I now take this into writing with what was the X, what was D, recall we introduced X's as a coordinates of the nodes of this element initial configuration. And we studied the case where X's were along this axis, and the X2 minus X1 was L, and Y1, Y2 were both 0. But I can take now a more general case and basically write it like this: 1/LE minus X2 minus X1 minus D2 1 minus D11. And then for the second would be minus Y2 minus Y1 minus D22 minus D12. And the same thing will go there only for the positive for the two other components times S11. So this was done for the element which was aligned along the x-axis. But if I take now any two-node truss-bar element and I have arbitrary orientation, I can define this X2 minus X1 divided by E will be cosine alpha, where alpha is orientation of this element. And then Y2 minus Y1 divided by E will be equal to sine alpha. It turns out that the same internal force will be again written this way. And I can then apply it to this one. Now, I don't have to stop with the two-node truss-bar element. I can go into the higher order representation. The only thing now you have to worry about let's say the corresponding computation of the Jacobian numerical integration and so on. So for example, if I go back with two-node truss-bar element, it always will be very simple, but I can also do it for a more complicated case where I have nonlinear. So let me show you this one, how it works. So there's a work that I've done some time ago, where basically we have something called consistent finite formulation of nonlinear elastic cables. That's when I was working in this École Polytechnique Fédérale de Lausanne. So we studied the cable structure. So imagine now if the cable structure is the curvilinear, and then you have it with your axis S, then I can start by building my virtual work equation by taking into account this curvilinear coordinate system, the coordinate S that goes from 0 to uppercase L, which happens to be length of this bar. And then in this curvilinear coordinate, I have this local trial with the t being the tangent vector, n being normal vector, and b being binormal vector perpendicular to t and n. And along these axes, I have a components that are v1, v2, and v3. So my Green-Lagrange strain could be written as dv1 ds plus 1/2 dv1 ds squared plus dv2 ds squared plus dv3 ds squared. I can write this in matrix notations dv1 ds plus 1/2 the vector dv, which has component dv1, dv2, dv3 ds times transpose times dv ds. Now, combination, let's say that the local curvilinear frame can be obtained by taking the derivative of the, let's say, your position vector with respect to s. This is your vector t. You have dx ds computed this way, and t is a unit vector. Then I can provide the n to be perpendicular to t, and in this, let's say, the plane that I choose. So then binormal b will be both perpendicular to t and n, and again unit vector. So representing this like a t transpose, n transpose, b transpose, that becomes like a orthogonal matrix, and I can transform from dv to du by using this orthogonal matrix. So in this term here, dv transpose ds times dv, I can do this transformation, and I can replace this term with the du transpose du because ds, because t times t transpose is identity. And then dv ds I can replace by t transpose, which is dx ds times du ds, and my final computation of the Green-Lagrange strain is given here. So why do I switch to this global coordinate and the global displacement? Because now I can interpolate that in the my coordinate system. Because if you have a local coordinate, the displacement vector changing from point to point, you cannot build this interpolation. But if I now switch to global coordinates, I can build this interpolation without any difficulty. I simply take now high order elements. It could be 3 node elements, 4 node elements, whatever you want. Recall if it was 300, it was 1/2 psi times psi minus square minus 1. Then it was 1 minus square, 1 minus square psi squared, and then there was like 1/2 psi plus psi 1. And basically, to this quadratic function, and you can easily represent your 3 node elements. So then I take either, let's say, I can take my the second law kickoff to be a word conjugate to the Green-Lagrange strain, and I assume the internal energy. So if I take some benign material, this will be 1/2 c times E squared, and my stress tensor will be C times E. I recall again, if it was very large compressive stress, I'm in trouble, but in tensile, I'm fine. Or I can take something like Ogden's incompressible rubber-like material, where lambda is a stretch, and mu and alpha are some kind of material parameters that are obtained from fitting this curve that you obtain. And this is more precisely obtained for an incompressible type of material. So basically, I can obtain now the stress, second pure Kickoff stress is a partial derivative of this guy. And with respect to strain, and given that lambda is equal to square root 1 plus 2e, you can obtain that this expression that is sitting here. If you want to be really clean with respect to incompressibility, you have to enforce that sum of these mu r times alpha r has to fit 2 times mu, where mu is, let's say, shear modulus of some kind of equivalent material. So one can then go into this interpolation and obtain the corresponding expression for your internal force vector and tangent stiffness. So let me go further. Basically, here's your the equilibrium equation in the weak form. This will give you internal force. That will give you external force. And then basically here you will have in the incremental analysis iterative updates, you will have your linearization internal force. You'll notice that you have here one part of the tangent stiffness. This is called material part of tangent stiffness. And then here you have something which is a geometric part of the tangent stiffness. And this will give you this external load. So basically, the geometric part of the tangent stiffness is computed here, these two terms. And then here I will need something like a tangent modulus, so it could be constant if I have a Samanan Kirchhoff material. So that becomes simply Young's modulus, which I called here C, or it could be changing in every value of the stretch if I have this Ogden type of material for rubber and stuff like that. So let me maybe just comment how do you actually go from one to another. You notice here that you have your ds. So how do you actually compute these things? Maybe I can make a comment on that one. First of all, if you have your interpolations, oops, so this is your true element. It might have 3 nodes. Let's say node 1, node 2, and 3. And you have measuring this the coordinate s. And then you're mapping this every point into the, let's say, isoparametric elements, which has these nodes which are 1, 2, and 3, that are sitting from psi equal to -1 to psi equal to +1. So this is your transformation S of psi. So basically then I have this true element placed in the coordinate system, which has a xi coordinates, x1 and 2 and 3. And I have my position vector sitting at every point here. And my shape functions are either 1/2 n1 will be equal to 1/2 psi times psi -1. So it's equal to 1 when psi is equal to -1 and 0 the other terms. Then n2 will be this bubble function, which is equal to 1 minus psi squared. And psi 3 would be 0 here and 1 there. So it's equal 1/2 psi plus 1. So what I can do when I need to obtain ds d psi, basically the idea goes as follows. I have to obtain first x I of psi to be equal to ni of psi times xi. That means basically I can have this one for x, for y, and for z. Just taking the coordinates of these nodes 1, 2, and 3 for x1 and for the direction x, direction y, direction z. Then what I can do here, I can take this to be a square root of dx dxi square. What is dx dxi squared? Well, first of all, if I want to compute dx dxi, that becomes simply the derivative of the shape function. This was a, and this was a, and this was sum of a from 1 to 3. That becomes the derivative of the shape function na dxi times the xa, sum of a from 1 to 3. So for example, the derivative of this one, dn1 dxi, obviously will be, here we'll be having 1/2. So psi square would be equal to 2 psi, and minus psi will be equal to 1. The derivative of this one will be minus 2 psi, and so on and so forth. So then you take the same thing for the dy dxi, only changing the coordinate x with the coordinate y. And you take the derivative squared. And then finally you have this one, dz dxi. And you take this squared. So this will give you a Jacobian. This will be your Jacobian, j of psi, that you define this way when you take computing this integral and switching from the physical coordinate to natural coordinates as you compute this contribution here. So this has been explained here. So these are your shape function. You can compute any type of arbitrary level of polynomials, 3-node, 4-node, whatever it is. You take Lagrange polynomials, product of these binomials. Then I take my strain displacement matrix that I call B here to compute first derivative of U with respect to S. And then if they have quadratic form, that will appear 2 times. And then basically I get my, let's say, internal force that I call here R to be a cubic function of the real displacement field. And when I do linearization, I obtain my material part and the geometric part of my stiffness matrix. So you can see that the material part is this B transpose times C times B. You can have like a nonlinear contribution of the strain appearing here. And geometric part is B transpose B times the value of the stress tensor. You can go into dynamics simply by putting a Lagrangian formulation. You put inertial effect in the fixed frame. That's just simple quadratic form. 1/2 velocity times what you call it, the density times the velocity, and so on and so forth. You can add very simply the computation of in the dynamics. And you have your mass matrix. So you have, instead of the static equilibrium, you have dynamic equilibrium equation that we'll talk about a little bit as we go along this week. So basically, then I was computing this, solving the cable and the dead load. And then I was computing this by taking the analysis of cable nets. We can have a vibration of pre-stressed cable, whatever it is. And then you get some kind of response and so on and so forth. So let me go back to this one. And oops, not that, no, I'm just a second. Stop share up. So maybe I can give you a homework. This could be nice to understand a little bit better what is going on. Imagine you have a cable of length L. You have Young's modulus cross section and initial length. And you first say by I'm going to pre-stress this cable such that my sigma is less than or equal 0.8 sigma y. So I can then obtain corresponding value of, I know that P of x will be equal to sigma of x, but I want to see what is the corresponding value of second Euler-Kirchhoff. And I call this one to be a second Euler-Kirchhoff in the initial configuration. So now I have stretched my cable, and then I clamp it here. So the behavior of this material would be S11 equal to Young's modulus times E11 being Green Lagrange strain, plus S0 that I obtained from pre-stressing. So this is the phase A. And in the phase B, I apply the loading. Which could be some kind of distributed load B2 if you want. And I want to obtain the corresponding displacement B for a loading, which is equal to B2. And you can take something that is suitable for you. I don't know, you can take this to be a steel. So it could be 400 megapascal. You can take something that looks like a cable. So it could be something like let's say 2 by 2 is 40, 40, let's say 20 times 20. I know it's not square, but what the hell? It will be like a 40 square millimeters, 400, sorry, square millimeters. Then E is equal to 2 10 to the power 5. And then what will we be to produce, you can try different displacement to produce something which is like, you don't have a maximum slope, which is equal to some kind of D max. D max could be like, let's say 0.2 L. So you're not really sagging too much when you're building like a pedestrian bridge that you want to cross. You don't want to be something that is sagging too much on DB2. So how about if you try to solve this problem and stuff like, and then if some kind of fat guy or whatever machine that is repairing the bridge comes in here and you already have people walking, the question is when you have this B2, what happens when you have another B2 plus 2 times B2? What will be the total loading? Or what will be total displacement, okay? Is that clear what I'm asking here? So you can go through all these steps to get the second law of Kirchhoff's stress. You can get this interpolation for deformation. You can obtain these elements. And please take, for example, what could be interesting is to take one 3-node element. So you have a better type of result with the shape function that I just plotted on the previous discussion. This is 1/2 psi times xi minus 1, then 1/2 xi times xi plus 1 for the right hand, and then 1 minus xi squared, and the one in the middle. And then you can try to see what is pre-stressing. This is the type of a phenomenon I told you. If you have starting with a pre-stressing, which is the case here, then you can put any type of result that you want here on top, and basically you can put some load on top and still have the stiffness. And that's basically the way we should try to get a bit of understanding. Okay, so if I now this was in tensile, and you can kind of practice a little bit on that one. But let me just go back and complete. If I have a very simple 2-node interpolation, so this one that I asked was 3-node. With 2-node interpolation, I'll have the following. I'll have my internal force written as this H transpose, this HB block unit matrix is 2 by 2 unit, 2 by 2 unit, and minus 2 by 2 unit, times 1 over LE, LE being the length of the real element, XE plus DE, XE being the coordinates, and DE being the nodal values of the displacement, times S11. S11 is equal to Young's modulus times the quadratic form in displacement nodal values. It's 1 over LE squared, XE transpose HDE, plus 1 over 2 LE squared, D transpose HDE. So if you linearize this, you get your tangent stiffness matrix. And so happens it has a material form. You can see that if you linearize, this will come down to your linear stiffness matrix. Will be like for the horizontal bar, the EA over L, then 1 minus 1 minus 1 is 0, or you have to split it into blocks 4 by 4, and not 2 by 2, because you're now considering not only displacement along the bar, but also perpendicular. And on top of that, you have geometric stiffness, which is equal to S11 divided by LE times H1. H the same matrix here. So let us consider a problem where you don't put bars in compression, at least not in tension compression initially, but you put it initially in compression. So there you have something called the instability problem. And I want to draw your attention contrary to the buckling problem. We have an Euler beam and you're doing the buckling along the beam. Here you can have something called nonlinear instability problem, where the pre-buckling displacement are very large before you reach this instability point. So what are you talking about? Here we are talking about shallow truss, which has these bars that are sitting a little bit inclined, so that the projection on the horizontal axis is equal to B, and projection of each bar on the vertical axis is equal to H. So if the length of the bar is equal to square root of H squared plus B squared equal to L, and each bar has a Young's modulus and Poisson's and cross section to be the same. And then we are studying the possibility of pressing the bar downwards, so with a force F and displacement V. So you can study this simple problem. It's actually statically determinate problem. And you can say that initially for the force equal to 0, displacement must be equal to 0. Then with increasing force, you're increasing the displacement. And then you come to the case where these two bars are horizontal, in which case V is equal to H if I put the axis H downwards. So V equal to H, these two bars are horizontal. And if you have a bar, you can take only force which is in the direction of the bar. It's like your wrist. If you lose the wrist, you cannot push your bone any other way but in direction of the bone. So basically, when you say the two bars are horizontal, the only force that you can offer in terms of internal force are horizontal forces, yet your force that you applied is vertical. So there could be no, let's say, external force, and there should be no internal force. So it means that you go up and then you go down in order to reach the zero force value for the value of displacement V equal to H. And then you go further, you keep increasing the displacement, you come to the value 2H, then you realize what you have is the truss which is turned now upside down, and you can say that the measure of the deformation is a stretch. All the other strain measures are computed from the stretch. In particular, Green-Lagrange is 1/2 lambda square minus 1, where lambda is the stretch. So if you take L, phi, and L to be the same, so stretch is equal to 1. Obviously, lambda square is 1 minus 1 is equal to 0. So I don't have any deformation. So whatever is the let's say X modulus, whatever, the stress will be 0. And again, I have to come down to 0. So I go down and I turn around, I come here. And after that, I can keep extending it. The bar becomes tensile, and I can go to infinity and have infinite displacement for infinite stresses. So I'm in particular interested in these two cases, where the determinant of my stiffness matrix, so here there's only one component, becomes equal to 0, because this is the kind of point that we call instability point. If you say that K is equal to df dv, then 1 over K is equal to dv df. So K become equal to 0, 1 over K will become infinity. So that means that dv over df going to infinity, if you have a very small perturbation of the loading, you will have infinite or very large perturbation of your response. So this is what is called instability problem that typically one wants to avoid. So basically here, when you compute this, I take my computational Green-Lagrange strain. This becomes 1 over L squared, x2 minus x1 transpose, u2 minus u1, u1 and u2 are order displacement, plus this 1/2, this quadratic term. So for the component which is of interest to me, basically I have a Green-Lagrange strain along the bar, which is equal to x2 minus x1 is equal to let's say you have this one, for the x direction, you have a 2, 2, 2, 2, 2. You have the projection is b, and for the y direction projection is a v, but the displacement is only in the vertical direction, so you only have multiplication with this y direction, so it becomes 1 over L squared h times v plus 1/2 v squared. For the homework, you can also try to work out this one to get the equation under control. So I don't have to go into detail because we are nearing the 12 o'clock. And then basically, I can then take this Green-Lagrange strain, multiply by the corresponding Young's modulus to get the stress, the corresponding cross-section to get the stress resultant. And then I can compute internal force according to the equation that we had for the general form of your bar. There could be any inclined form, so with the x's and y's corresponding coordinates, which are here. As I said, if you put your x here, it will be like 0, 0, it will be like b and h, and so on and so forth. And so when you finish doing that, you get internal force vector, which is this internal force, equivalent internal force vector multiplied by h plus v, which is coming from this extra term. And you have two bars, because symmetry, so you have a 2 times EA divided by L to the power 3, h plus v times hv times 1/2 v squared. Then I can see really that this should be canceling for h equal to minus v, and h equal to minus 2v, because when h is equal to minus v, this first term cancel, and when h equal to minus 2, v is equal to minus 2h, that becomes minus 2h squared, and it becomes 4h squared divided by 2. This is plus 2h squared, so they cancel, and you really recover what you had here that you obtained directly from the equilibrium. The only thing is now we take the proper, let's say, signs, because x and y are horizontal and y is vertical. So v is actually negative if you push it down. So that's why you have this type of value here. And then I can compute my tangent stiffness. Either way, either I take derivative of this one with respect to V, or I go through the adding material and geometric part, and I obtain this to be equal to 2EA divided by 2 power 3, H plus E squared, plus 2 times N divided by L, where N is this internal force that I already computed here. So then you ask yourself, when do you actually have this instability? When the K is equal to 0, and this is actually quadratic equation V, so you can compute these two values, that V critical is equal to minus H times 1 minus square root of 303, or minus H 1 plus square root of 303. That means you are actually sitting here, you're either minus 1 minus the square root of 303 times H, and this is 1 plus square root of 303 times H. And then you get the corresponding critical value of these forces, which is equal to minus 0.3849, and so on and so forth. So you can obtain that instability here, contrary to buckling, occurs with a very large deformation. So 1 minus square root of 303, square root of 3 is 1.73. Let's say if it was 8, you divide by 3 is 0.6, 1 minus 0.6 is like 0.4. So you're talking about 40% of the height. These are significantly very large displacements before you come to the critical point. And this is 1 plus 4 and so on and so forth. Again, you have a critical point with a very large pre-buckling displacement. And you can try to compute this with a, let's say, linear instability, and I assure you get very wrong result, because typically this nonlinear instability is something which is very heavily influenced by the large pre-buckling displacement. You have this type of thing also when you go for plasticity, you have necking and stuff like that. So we study this as we go along. So here I actually stop here because tomorrow when I talk about this constrictive modeling, it's good also to recall this material which was spatial description, a large displacement, and basically cover there. So what I covered in today's lecture, skip all this, was the fact that you have a nonlinear mechanics in large deformations. The main source of the nonlinearity is kinematics. Then we use Lagrangian formulation as opposed to fluids guys using Eulerian, or other guys using updated Lagrangian co-rotational. The deformation gradient is the first intrinsic measure of deformation. It's a good measure for large deformation, and that you can have many other strain measures. And the typical replacement of this true or Cauchy stress in the strong form is the first Euler Kirchhoff, in the weak form is second Euler Kirchhoff. And we try to illustrate what happens with a simple Sandana Kirchhoff material written in many books that actually is not good for large compressive strain. So this is roughly what I wanted to say today. It's 12 o'clock, so we'll pick up tomorrow at 8:45 and as we go along. So let me stop here and ask you if you have any questions or comments to kind of elaborate a little bit what was not clear enough. All the homeworks, I guess, are clear, right?
Professor,
Yes.
at the beginning, you talk about some example,
Yeah.
logical example. Can you explain a little bit more about that applications?
Which example in the beginning you said?
You said that about practical examples about large rotation and large deformation.
But
Applications.
well, large deformation, large stuff is really everywhere. If you have, for example, very slender structures moving a lot, for example, you cannot apply linear theory. Let me put it this way. Okay, stop share, just a second, up, stop share, and go to the whiteboard. Anytime you have a situation of this kind, let's say, up. This is your truss bar, and it has length L. So if I extend it just a little bit, and I say that deformation epsilon is equal to du dx, you're just fine, okay? And we said if you want to have a small displacement gradient theory, the absolute value of this, absolute value of that has to be much smaller than 1, okay? But this is this 1D case. But I said when we study large deformation, so it means that L phi, which is obtained like, this is your L phi here, is equal to epsilon. Let's say if it's homogeneous, it's basically 1 plus epsilon times L. it's almost the same as L. Yeah. Now this is okay, okay? And if I want to have a large strain, I have my lambda to be a stretch, which is L phi divided by L. And it could be very different than 1. Okay. So every time now I have this is also L, but let's say I'm moving the bar like this, and I'm moving bar like that. So this is the form configuration. This is L phi. So if I take a small deformation theory, epsilon will be basically here equal to 0. Because I move this end vertically and I move this end vertically, and I don't really see any difference in the x direction. But if I take lambda, L phi is certainly not the same than L, and I can really take into account the stretch and use that. So whenever you have like a very large rotation, you have to go to the large displacement theory. And this is something that you can handle with the beam, plates, and shells, you know, when you have these type of things. And the theory, which is geometrically linear, is not only restricted to small strain, but it's also restricted to small rotation. So applications are from computing the slender structures, satellite antenna, whatever it is, airplanes and things like that, and then computing the technological process where you need pre-stressing, for example, thing like that I gave you for homework. So you have a large deformation setting defined, and then some. Today, for example, it's very fashionable. It used to be time, and none was the king. Nowadays, is life science is the king. So I've seen many papers where people revisit the behavior of the large deformation theory for solid mechanics, and the so-called soft materials. So the tissue is deforming a lot. So you have robots which are deforming as they walk and things like that. So in biomechanics, you have a huge number of these applications. And then slender structures that you have like airplanes have to be the thinner the better. So that means they have very prone to instability and things like that. So and then satellites and whatever flies has to be light. The birds are very light. You know, if you catch a bird, you keep it in your hand, it's very light. So basically, you have a number of these applications that are typical of large displacement, large deformation, for sure. But depends on the particular domain. You know, that's what it is. Okay. Bioscience today is really very huge business of they call soft robotics. You know? So you have revisiting many of these formulations that we had, and then getting the things in, you have like, you know, the model arteries. There's a guy I know, he was using Ogden model for rubber to model the arteries. So what the hell, I said the arteries should not be rubber, but you know, they're actually fiber-like materials and stuff like that. So it becomes quite complicated when you have this type of modeling. But at least hopefully the interest of modeling of this is very large. So that's the applications. Going from one domain to another, you can have many. Whichever one you like the most, huh? Instability, for example, is one that you looked at. Okay. Yeah.
Yes, Professor.
Any more questions or comments? Okay. If no question comments, let us then convene for today, and we meet tomorrow at 45. Okay, guys. Sure.
Thank you, Professor.
Okay. Bye-bye.
Bye,
Have a peace.
Professor.
Yeah.
Bye-bye.
Thank you, Professor Bon.
Bye-bye. Then did you come up with your presentation? The one that
Yes,
you, yeah.
I don't.
Huh?
I don't. I want to show you something, but
Just
well,
see.
yeah, see you sure because it's something about my job. But I think he's not there.
He's sleeping.
Jishuaki.
Okay. Can I kick him out? Can I kick him out? Participants.
Mm.
Oops, no.